I think the last place we stopped at, did, you get, David, did you get that off, that link off to AJ?
That MSN was the new one, right?
Yep.
Yeah.
And Stevie there?
I'm here.
Toot your train horn. Wait. Okay, Isaac's here. I think we were the last place we were at, we were talking about with Isaac. Is that right? You were up the bat? And so I'm telling you that the damper, open motor control, everything works just fine. But in automatic and manual, this does not work right here at all. It doesn't go up and down. So if the thing is, where do you start troubleshooting? It's probably where you start with this. And the first thing I ask myself, well, what doesn't work? What's the first thing I see that doesn't work? Well, if I look at it, this here indicator ain't going up and down. I can start there. So now you got to find out what makes this guy go up and down. Well, we got to have 0 on one side and some kind of voltage on the other. Somewhere between the difference between 10 and near 0. And if this wiper's all the way to the top, it's going to get 10. If it's in the middle, it's going to get like 5. If it's at a quarter of the way, it's like a 2.5 volts. So you get the idea. That's what it takes in order to make this thing work. So this comes from a power supply, 12-volt power supply. DC, we went from 120 volts coming in and converted that to 12 volts DC, like a car battery voltage. And so, and just like a car battery, it's got two poles. It has a negative and a positive. So, and you know that and so we're putting in a negative and a positive across a known load. That load, there's 2 loads there. This here load is in parallel with part of this load here, depending on where the wiper is set up.
We're not seeing what you're pointing at, Clarence.
Okay, thank you.
Take the mouse. There you go.
Any better?
Yep, now we see it.
Crazy. Okay, power supply converts 120 volts AC. That means it takes a transformer. Transformers are down from 120 volts to 12 volts to AC. And inside there is a rectifier, those diodes. I think that looked like that sounds like an electronic check valve. Well, it turns that into DC, so your voltage, your current can go in only one direction. That's why they call it DC, direct. You know, it only goes in one direction, just like your car battery. So anyhow, that means it's got to be polarized. And so on your car, you know, you got black for the minus, and we're going to do black for the minus on this one here also. So with your meter, what are you going to set it for, and where are you going to put your where are you going to clip that on at? Isaac?
Yeah, so you're going to set your meter for DC.
Good. What kind of voltage range?
12 volts.
There you go. So something for 12 volts. Got it. And now where are you going to put your test lead?
On your negative, or your black one will go on your negative.
Okay, your -2 right there, the power supply.
Yeah, yep.
Okay, works for me. Okay. So now you see the symptoms. Where's the first place you're going to put your probe?
I'd put my probe right on 4 right away. Or I guess first test it. I would test it.
Okay.
Make sure your meter's working, and then I'd go on to 4.
Okay, so you go from 2 to 1, testing it. Yeah, got it. 2 to 4. And I'm saying you've got 12 volts.
12 volts there.
Yep.
Okay, so that's a good reading.
Is that a good reading?
Yeah. Yep. I guess, Clarence, what was the question? Was it the damper or the actuator we're going on?
It's this indicator right here.
Oh, okay. Then I wouldn't
Going
even
up and down.
Okay, I would have just went right to 13 then.
Okay. So going right to 13, what are you expecting here?
12 volts.
When?
When actually no. if that's in the middle, that'd be 5 volts.
Okay,
It'd have to be all the way open in order to have all the volts going through it.
okay, so you got your pot set at in the middle. And you're checking for 5 volts. And I tell you that you've got,
Wrong.
what's that? 6 volts.
6 volts.
Okay, 6 volts. So now, you got 6 volts. They're at terminal 13. I'm saying you do.
Okay, yep, no, that's a good reading then.
Okay, now where do you go?
Now from there, would you jump over to 3? Well, that's kind of your, well, yeah, 3.
Okay, you've got your lead here at, you got one lead right here. You're expecting 6 volts here, and you're getting 6 volts there. It's in the middle. You know that 3 is good, because if 3 wasn't good, then that one be reading 6 volts there.
Okay,
So it's good at this point. So now you have to, now what's expecting to be reading that 6 volts? That's not working for us.
your damper position
The
meter.
meter itself, the meter itself. This is this is that meter right here. It ain't working. This ain't working. You got 6 volts here. You got a terminal on the back here, don't you?
Okay, okay,
Okay, can you check out that terminal?
yes, you can, yep.
What are you expecting there?
It should be 5 volts or 6
When?
volts. When you're at wherever your actuator's at, if your actuator's opened
No,
halfway.
when they're, yeah, your actuator, yeah, or where you got the pot set, you're right.
Yep.
True, when the actuator's in the middle. Okay, so I'm gonna ask you again, what are you expecting there? And you're gonna say 6 volts when the actuator's in the middle. Okay, here we go. You ready for it?
Yeah,
What-
yep,
What are you expecting here?
6 volts. When the actuator or your pots is halfway.
There you go. That's what I wanted to hear. I wanted to hear the complete story. You're leaving out the good part. The part where the good guys win. Good guys
Right.
win.
Right.
Okay. I think we beat this guy up pretty damn good. And so
No,
now you
it
guys
may
also
be a brand new meter that
What's-
was
what's
not
that?
adjusted yet. Some of them you can adjust range on to tell it that 6 volts means 50%. Some you can't. If it's a digital one, you probably can adjust the input.
Sometimes they give you little choices like that. This is for this simple circuit, works out pretty good. Anything else you'd like to add to this, Steve?
A lot of times, if it's a system like that, they may have already stuck a trim resistor in ahead of time. So you're actually dealing with 0 to 10 volts instead of 0 to 12. It's just a whole lot easier in your mind if you know you got 9 volts, it should be 90%.
Take some time, pull out your damper control drawing, look at them, try to figure it out. It's a game, it's a puzzle. See if you guys can be on top of it. If it's not working. If it's overreacting, you know, there's stuff you can do to keep it from overreacting. But make the damper control work for you.
Remember what I was mentioning last week when we were talking about if you've got an erratic signal and you've calmed out everything you can electrically, take a look at putting that damper probe into the bulkhead of the dryer. It may be that you're just getting a pulse in the signal to the photohelic that it can't follow. And a smooth airflow on that probe may help settle things out. Back to you, Clarence.
Okay. Okay. I think we're probably ready, set, go. Take a look at our DC control.
Seeing both of them.
Yeah. And you can zoom in on the right if I ask you to, but you don't have to. That looks pretty good. Okay. You're going, what the hell is this? And Nathan, do you got DC motors on your bins or variable frequency drives?
I believe they're DC.
Okay.
Could even be the old Boston gears.
Do what, Steve?
Could even be the old Boston gear reducers if it's got the original ones on yet.
The green ones, God, I don't know how we'd get those things fixed. I used to fix them and make some pretty good money.
We've had to replace some motors because we weren't able to find the original motors for them or fix them.
Not
They-
unlikely.
They may be on the VFDs then. Okay. How about Jess? Do you think you got DC motors or variable frequency? Jesus.
It looks like 120 coming into a 120 AC's coming into a DC motor.
Oh, here in the drawing, okay. But at your plant, do you know at your plant if you got DC motors or AC motors?
I believe they're AC motors.
Okay, they call them like variable frequency drives, maybe. Yeah, you ever hear that before?
Yeah.
Okay. How about you, Isaac? What do you think you got?
We got VFDs.
Okay, so
DC on the slat though.
okay, you got DC on what?
On our slat.
Slack conveyor?
Yeah, we haven't switched that over to VFD yet.
Okay, so you got a variable speed slack conveyor?
No, we do not. No, our bins are freak drives, or VFDs, but our slat is not.
Okay, sure, I understand that. Okay, anyhow, we're picking on variable speed, whether it be a VFD or a DC motor control or a eddy current. Yeah, this is all kind of the same. They all kind of function the same. They're all going to want to have a start signal. They're all going to want to have a speed signal on how fast to go. And they all require power. So that's the input it needs. And so if you look at this little black box, the DC motor control, on the top, side, and bottom, this is the inputs. And if these inputs aren't doing the right job, that DC motor shaft is not going to turn. And say, well, what does this DC motor require anyhow? Well, it's got two different windings on it. It's called an armature winding. Another one is called a field winding. And the field winding, you're going to say, oh, look at that. It says field plug to field spine. That's 90 volts DC is what comes out of the DC motor control to your field. And it's there all the time. As long as you've got the input of 120 volts there, you'll always have 90 volts DC coming out of there. But the other winding, this is the one that changes from being off altogether to some kind of a voltage in between 0 and 90. That's the armature. And so and if you vary the voltage to that, and so you're gonna have a variable DC coming out of that DC motor control. So you're going to have 0 to 90. So if you want to go half speed, then you get about 45 volts that sends out. Full speed sends about 90. So that's what it takes in order to get that thing to turn and turn at specific speeds. So moving right along now, then we've got, and in order for my armature voltage there, I have a switch there on my lights. Those lights there, they're kind of what my armature and my field. So the more light that you have, for the armature, the faster it's going. The field is always gonna be bright all the time. So this is the outputs we're gonna be looking at to see if this thing's working right. And so that's the output of the DC controller to the motor itself. And another thing that's going to, as far as that armature voltage, things that's gonna change that is that start-stop switch there is gonna tell us to come on or off. And then the other thing there is we've got a pot switch up there, or not a pot switch, but a pot. And then so that pot, the more that you turn it, the faster it's gonna go. So in the clockwise, that should say counterclockwise, David, FYI. If I got that wrong, I'm sorry. But in the counterclockwise position, that pot would be turned all the way to the left. And that means it would go at full speed. That means that that wiper is going to go from the position it has right now. If you can see my arrow, can you see my arrow?
Now you're moving it.
Okay, so that arrow that it slides along, it's gonna get closer to the top that's high of this 10 volt DC. This is a power supply, 0 and 10. And then your load is that pot. And then and if you've in this particular circuit, you're gonna put your lead on the low side, on the negative side, if you're going to be testing this pot. And then so we've got to have this pot set something off of 0, so that we know that we're expecting some speed if we're in case expecting this motor to move at all. Stop start on the bottom here is okay. We want to come on, we hit the start. And then from that, we want to stop them, we open it. These are momentary things. And consequently, it's got little inputs there in order to figure out, what's going on. So there's little voltages between 10 and 9 or 10 and 8 that's going on. I don't know those, but maybe if that's the problem, instead of checking that with a voltmeter, maybe we check that maybe with an ohm meter is what maybe we would do. So if I'm saying I'm expecting this thing to turn, and maybe we can take a look at what we have on our diagram right here, our picture. We can see all these terminals, 8, 9, 10. You got 8, 9, 10. You've got terminals here, 3, 4. You got terminals over here, 5, 6, 7. You've got your coming in with your power 1, and then we have our start-stop switch, 8, 9, 10, which is going to go up to here. So one of these things is going to have a wire to it like 10, and here's one that says 9 probably.
You can scroll in and see.
I don't think we got to go above that point. These guys can kind of, yeah. Zoom in on it. Now that you're there.
9 and 10.
Okay, so like here's your 9, 10. It goes across your stop button. So physically, you can tell me where you're going to want to be putting that when we do some troubleshooting. Zoom in a little bit on that pot if you would. Here's your pots, 5, 6, 7, which is the same 5, 6, 7. See, these wire numbers match up with the terminals. So those terminals that we have over there, they end up going to terminals. And then from the terminals, we can go up there to the these outgoing terminals right here. We'll now go to the terminals that's on the board here. So you can see 5, 6, 7 here is going to be going up to.
Well, they're on this side, I think. Yeah, there's the wiper and pot low, pot high. I think
Okay.
that's 5, 6, 7. It's hard to see right here, but
Okay, So this kind of gets you guys familiarized a little bit about, when we do some troubleshooting, you start looking around, but no, we gotta be taking a look at the schematic. And so we now familiarize ourselves with it physically, and so this helps get the job done. So, I'm gonna be picking on probably, let me go with Nathan first this time. I'm gonna say that my symptoms are the, motor doesn't turn. And, so basically I hit my start button. I'm expecting the motor to turn. That means if the motor's gonna turn, that means this armature here has to be lit up somewhere. Then I'm expecting this here light to come on for the field voltage. So I'm gonna say that our field voltage is there. Our armature, we're expecting, depending on where we put the pot. So, we'll say we put the pot in the middle. So if it's in the middle, then I'm probably expecting 45 volts are going to the armature. And so I'm telling Nathan I'm hitting my start button. Before I hit my start button, I can see my field voltage is on. Is that good? Is that in a good working DC control motor circuit? Is the field, should the field voltage be lit up before we even
No.
start it up? And the answer is yes, it is. Yes, you've got field voltage there all the time, and I don't expect you to remember that, but that's what happens in a DC motor. You have to see what kind of you have, and then you study that one. But in this particular case, this is what you do: is you have and so 100 volts is required, and it is there. So that's good. So now I hit my start button, and I'm saying that my armature voltage, or I don't see any light at my coming on. And then I would ask myself, well, what kind of voltage should I be having with my light? Should it be dim, or should it be half dim, or should it be on all the way? What should it be? And so, and what's going to tell me how much voltage that I should be getting here at my armature? What setting do I have on my circuit that will tell me what voltage I should be having here?
DC.
Okay, what you would be looking is at the pot. So if your pot's in the middle, and then you should have about 45 volts. Okay, if the pot's all the way to the top end, maximum speed, you'll have 90 volts. If
Okay.
your pot's all the way to 0, you'll have how many volts?
On
On the armature. Armature, I said half pot, you should have 45. Full pot, you should have 90. At 0 pot, I should have how much voltage?
you'd have 0.
That's right. Okay. So, we're trying to see if this thing's working or not. We have to push the start button, but just because I hit the start button doesn't mean it's gonna turn right. Is that right, Nathan? Because of why?
Because
My speed pot might be set too low. Dig it?
okay.
Okay. So just because you hit the start button, don't expect that thing to turn if your speed pot's at 0. Is that right?
Right.
Okay. So I'm gonna tell you I'm putting my speed pot at 5. And I press the start button. And then I'm gonna tell you my armature or my shaft is not turning. And I check here at my outgoing terminals for my armature. I'm expecting it to read 45 volts and I'm getting 0. So that's a bad reading, is that right? If I'm getting 0, and I should have 45 because of why? Because of speed pot setting.
Yes.
Okay. Okay. So I'm saying you've got 0 there. There at the armature. So So just because you set this pot there at 5 doesn't mean it's working right, maybe, huh? Because this thing here right now is saying 0, and you gotta make sure it's, this has got its proper inputs. In order to get 45 here, you gotta have power here. You have to put your start, or hit your start button, and you have got to have your speed signal. So we gotta prove we got our speed signal. So how's a good way to check to see if you have our speed signal?
Our speed signal.
So look at the terminals. What kind of voltage are we talking about there? Isaac, can you help out? What kind of voltage are we expecting there on that speed signal?
DC.
And what's the maximum we're expecting?
Well, you're at 5, so 45.
Okay, okay.
Oh, 10
what's
volts.
that? Okay, 10 volts. So if we're gonna set our meter, where would you set your, where would you plug your lead into for your, would you put it into the black lead or the red lead? This is polarized. This is. With your black lead, that's like your negative on your car battery. What color is that?
That's black.
So you're gonna alligator clip your black to the negative side of your circuit. What number is the negative side of that circuit? 5, 6, or 7?
Oh, let's see, 5, 6, or 7. 7. Yeah,
Okay.
7.
Okay.
Positive would be 5, so you'd be jumping over to 5 to check.
Black.
Okay. Are you hello? Okay. How you doing, AJ? AJ is kind of zooming in. I'm starting to, so right now what we're having is so we want to prove to ourselves that this here DC motor control is getting the right signal. So if we go from Isaac, you put your one lead on 7. Where are you gonna put your other lead at?
5.
And if you put it at 5, I'm gonna tell you that you've got 10 volts there. Is that a good reading or bad reading?
That's a good reading.
Okay. Now that you prove that you got the power supply going to the pot so far, what's your next move gonna be? Okay, remember, we're expecting 45 volts at the armature. That means we're expecting to get half the speed signal to that DC controller. Have we proved that yet?
No, we haven't.
How do we do that?
Go back to the armature.
Okay, no, the armature there, 3 and 4, was at 0. And so we're not gonna go back there again. We gotta find out the output's not there. We gotta find out, we gotta prove that to make sure the inputs are there to do the job. One thing is the speed signal. And we haven't proven yet that the speed signal is getting to the DC motor control. Yet, have we?
No, we have not.
So where is that 5 volt signal we're gonna check to see is going to the motor control? Or the DC motor, where do we find that?
You'd have to go to the right of 3 and 4, wouldn't you?
Okay, here you got one of your leads. Do you see my probe?
No, I'll click the screen. There you go.
Okay, okay, so one of your leads is right here. If we were, see, here's your 10 volt power supply.
Yep.
And then you got high pressure seeking low pressure. So you got 10 volts here, 0 volts there. This wiper is gonna pick up right in the middle, that's gonna be 5 volts. And there's 3 terminals right here. It says pot wiper, it says pot high, and it says pot low. And it goes to these wires right here. This is actually a 10 volt power supply right here. So you got, this is on the negative side of the power supply, that's on the plus side. So you're sitting right here with your probe. Now, if you want to get back to as close to the to the power supply as possible, you could be putting your lead on the pot load terminals, this right here. So if you go to pot load terminals and you expect, and here's the wiper terminal, what are you expecting at the wiper terminal? How many volts?
5.
5 volts. So what I would have done was put my lead here, right here in the pot low there, stuck it on there, and then see if I had 5 volts. If I had 5 volts, then that's the proper input to the DC motor control. That tells me it has its proper inputs. So therefore, as far as the speed goes, if it that pot wiper thing is working. But if it's not there, well then I know it's the pot. So with our lead here at the pot low, and I'm going to tell you at your pot wiper there that you have 5 volts. What does that tell you?
That tells me that everything there is working.
As far as the input, what does that tell you about the DC motor control? It tells you, well, it proved that signal is good. That means maybe it's the stop start over here. Maybe I have to troubleshoot with the stop start. Maybe I haven't asked it to start yet. But typically, the start stop has got nothing to do with a pot low. So if that's a way of proving if you've got the right inputs or not, that one in particular. Okay, let me pick on Jesus here a little bit. I press my start button here, and I'm sitting at in the middle for 5 volts. I'm expecting to see my light here to come on real high, or at least somewhat, because we got half speed, and my field voltage comes on. But so I can see that my light's not coming on. I just got done proving that my hot signal made it to my DC motor control. So and I know I got voltage coming in because I got a power supply here. That process of elimination was the fact that we've got this start-stop switch here that maybe we haven't asked it to start up. And so we could be checking things with voltages, but we don't know what the voltages here are. They didn't tell us that. We knew up here, so we could troubleshoot it. So maybe we'll just do this with an ohm meter, because we can just kind of check to see if those switches work. Because we know a switch is like touching your ohm meter leads together or have them apart. We also, so hey, Suits, if you were going to do some troubleshooting, and you guys can help some troubleshooting with stop start switch, you wanted to prove that the inputs were good, where would you start? I wonder if you're going to do that with an ohm meter. First of all, about the ohm meter, do you do it with power on or off on your on the DC controller?
Or off.
Yeah, you have to have it off. And another thing to remember about when you're checking things with an ohm meter, you have to, what else do you have to do for that circuit to prepare? For an ohm meter.
Make sure you're in DC.
Okay, well, you have to make sure that it's isolated. Okay, so you got to take your ohm meter and you say, okay, I'm going to go to ohms. But now you got to say, I want to make this measurement here, but you got to isolate part of the circuit, because otherwise you're going to go through the other part of the circuit. And so we're going to be proving to ourselves that this stop start switch works. And, but we got to isolate it, which means we got to take a wire off. What wire would you guys take off if we were going to isolate the stop and the start and do some testing? Test the start and the stop. What would you do? How would you isolate it?
I'd take off wire 8 and 10.
What if I told you you could, it's a lot easier to pick out if you just do one?
10.
Okay, so if we did, if we took off 10 by itself and left 8 and 9 there, because that's in common to both of those for your testing. So if you put one of your leads on your ohm meter on the one that came off a 10, can you do that in your mind? Can you envision that, taking that out right there? Put a lead right there on the wire. And we there's no power, you may make sure that's turned off. You just isolated the thing. And so now you set your meter to ohms. And so across a closed switch, how many ohms would you expect to see there, Jesus?
A closed switch, you would expect to see no resistance.
0, okay? Terrific. You expect to see 0. And then if you put, and then if you put your, it's like touching your leads together, right? What are you gonna read with your ohm meter if you put your leads together?
Not OL.
No, when your leads are together. How much resistance do you have? 0 resistance. If you pull your leads apart, what do you got? OL. Infinite, okay? So if I'm going from 10 to 9, is that a normally closed switch or normally open? A stop button.
Normally open.
The stop button,
It shows closed right now.
so it's normally closed. That make sense? How about the start button? Is that normally open or normally closed?
Normally open.
Okay, the spring loaded. Okay, so if that's normally closed, if I go from, and you're not touching it, with your ohm meter, 1 on 9 and 1 on 10,
Should show 0.
you're gonna see 0, right? And with your meter still hooked up that way, if I push that stop button, what are you expecting it to say? Your meter. OL, okay? See the difference? Did you
Yeah.
just prove that that stop switch worked correctly?
Yeah.
Okay, so that's not the problem. Okay, what if I put my so now let's check out the start button. So if we're gonna start with the start button, what 2 terminals am I gonna be hooking up to?
8 and 10.
Okay, and what are you expecting on 8 and 10? What kind of reading?
Looking at the graph right now, you see OL on your
Good
on-
job. And then what if you push the button?
you should receive 0.
You just operate, right? Operate correctly. Did you just check that out with your ohm meter?
What's
Yeah.
that?
So you just checked that out with your ohm meter. I just want to say you did a good job. Nice job.
Oh,
Okay. You did a good job of checking it out. Isaac, you did a good job of checking it out. Nathan, we were working with the armature voltage you had, and so these are the 3 inputs that we need in order for this to work. You need to have your, you have to have a speed source, you have to have the power to it, and you got to ask it to come on. And so any one of those things could have kept that from happening. And we could have been checking, at 5, 6, or 7 terminal there, or right there on the pot leads. Say that let's pick a Nathan again. So I press my start button, or before I even do that, my field is on. So that's good. I'm happy with that.
Right.
Now I hit my start button and my armature light doesn't come on. So I'm expecting something to come on because this here is sitting at 50%, my speed pots. And so that's not. So I gotta check to see if we started it up in the first place and then or if it was the speed pots not working right or set wrong. But we look at the knob and it's set right. So we're gonna be putting one of our leads on the minus side. So we're gonna set our meter for what? Is this AC or DC, Nathan?
It's DC.
Okay, it is DC. So this is the negative side. This is our power supply here. So we're gonna, there's a terminal here, right here, that says pot low. So on here, we're gonna be putting one of our alligator clips, and that's gonna go to the low side of the power supply. So with that alligator clip hooked to the pot low terminal, we hook the other lead to what color probe that we got.
The red.
No, we're gonna do the black. We're always tying our circuit to the low side of the circuit, and because the DC is polarized and that's negative, that's typically what we're gonna do. So you're gonna take your lead and then hook it up to the negative side of your meter, okay? That means you're gonna be probing around with the with the red one. Right now, we want to prove to ourselves that the signal here is working right for us. And so if you check right there at the DC motor control, that's where I would check for it. Not at these terminals out here, not at the pot. I would check right here because this is where it's looking for the input. So right now you got one of your leads hooked up to the negative side of your meter, and now you're going to be probing. So where would you probe? You can probe any place in here. And you tell me where I should do the terminals on the DC motor control, or the outgoing terminal. Where? Where?
My picture is blurry. It's not letting me really see any.
Okay, okay. I'm gonna let Isaac take over from there. Where would you do it, Isaac?
You could go on to your pot high and you'd be looking for 10 volts there.
Right here on the DC motor control.
Right.
Good job. And I'm saying you got 10 volts. That's a good reading, right?
Correct.
Okay, and then, but maybe before I even did that, because this DC motor control is looking for a signal, and this is signal being there or not is what's really going to kill it. And so you know if you got power here or voltage here, you're going to have voltage over here. I'm just trying to save you a step. See where I'm going with that?
Yep.
So how much are you expecting at your wiper?
5 volts.
Okay, and I tell you got 0. What does that tell you?
That pot's bad.
Not so far. What do you have between that and the pot? You got a terminal, right?
Oh, okay. Yep.
Okay, and what if I tell you that you have 4.5 volts there?
Then that's a good reading.
That's a good reading. So you had a bad reading here, a good reading there. What does that tell you?
Your terminal or your wire.
My wire between 6 and wiper?
Yeah, between
Wiper and
pot 5.
pot 6.
Oh, okay. Yep.
Okay. And so that would be a problem. What if I told you that I had no reading here at number 6? Where would you go?
Then I'd go back to pot 5.
Okay. Yeah, that could do that. Pot 5, yeah, pot high right there. I'm saying that you've got I'm saying you got 10 volts. And that you've got 10 volts right there as well. So but those are good checks, yes. So I'm saying you got 10 volts there and 0 volts there. So now what do you do?
God, if you got 0 volts on the other side of 6, I'd still. It's kind of the point where your wiper's bad, ain't it?
Okay, yeah. So now you instead of checking here now, you're going to the hot wiper right there. Do you see where my probe is?
Yep.
Okay, so, yeah, and so at that point, I would probably say that you got 4.5 volts.
Okay, so you have 4.5 volts on by 6, so I'd say now your wire would be bad.
There you go. Or if I told you you had 0 volts down here, what would that tell you about the pot?
The pot's bad.
Maybe the pot's bad, but maybe you never got the 10 volts to the pot in the first place. So maybe you gotta be checking both pot high down here as well.
Okay,
Because if the wire's broken from here to here, you aren't gonna read anything from here to here.
right, okay.
Okay. Okay. Well, I think we kind of beat that up pretty daggone good. Sometimes we play games with guys that when we do this right here, we will take one of these bulbs and we'll unscrew it. So it's just sitting there. So they check their field voltage going out. Well, I got field voltage going out there, but the light still ain't on. And then there's and so that could do it. Or we got this little pull chain thing here. Sometimes we pull that out and we got power right there, but the light doesn't come on. And then, but it's hard to get under here to do the testing. So then we cheat and we tell you. So that kind of takes care of what we're doing with DC motor control. I know that Steve wanted to go over some things with you yet some more, and we can do that some more. But I do want to introduce our friend AJ. AJ, how you doing?
I'm doing good, Clarence. Can you hear me?
We can hear you. You're looking good. He's back to the racetrack.
I finally got the audio turned on, but yeah, you're looking good, Clarence. Sound good.
Yeah. Well, it's nice to see you. I understand that AJ, the reason he looks so good is because he gets to go to Con Expo and he's married.
Yep.
That sounds trouble taking your wife to Las Vegas with you.
What was that, Clarence?
That sounds like trouble taking your wife to Las Vegas.
Yes, I am.
We'll have to get you to stop by Area Systems and at their booth, give you something on that. Okay, since the last time out, we so tell me what you what what I want to do here a little bit also is I don't know how hard it is to pull up, but I do know that we have got some prints on some of the BNS control systems. Not that I'm peddling BNS, it's just that by going over some of the schematics, that helps us to maybe understand some things. Is that hard to find, David?
No, I'll just take it. They're not really labeled good, Clarence. These are the drawings.
Just click one.
Okay.
So you can get that thing and take up the whole screen. Yeah, we can definitely do some zooming. If I were to look at this, let's see, what is this one here for? It looks like it's a cold feed bin, basically what we're looking at. So this might seem all Greek to you, but if you look at the top part of this, you're seeing L1 and L2. This is the power going into a blending control system. And this is a part of the circuitry or that is under your cabinet. And it has all those input outputs to it. And so we're actually going from one block to one block to another, connecting boxes. And that's basically what we're doing with these components is they're boxes and they have inputs, outputs, and away you go from there. And so this here is going to require 120 volts to it. You can see that coming in the top there. If you can slide down there a little bit, then David. And then you see those terminals on the side there, that's your motherboard. That's where all this out and stuff on the, so that left column there over there is actually the motherboard with the terminal strips. And then on the right there is the things that are kind of tied to it. And so let's look at TB 2-4. This here says like feed or run. And we're and then we and we've got to energize a relay for that. And we have a choice of if we're gonna energize that relay automatically or manual. Well, automatic, if you have a switch in the automatic position, TB 32-4 is going to have 120 volts when the computer says that we want it to be on, and then it's going to go out there to that. So it goes to that TB 32-4, which is right here. If you guys aren't following me, if you can see my thing, and then it's got 120 volts here. And if you're in the automatic position, it will take off automatically. And it energizes this. This is a relay. You got yours L2 on one side. If you put a hot on the other side, or if you put it manual, you got a hot the other time. It'll energize. This is a relay, and that relay set of contacts is then going to close something between terminal 19 and 20. So at 19 and 20, there's an Allen Bradley VFD. This is a VFD. We're telling this VFD to run. This is what's happening here. And here's the VFD here. It's got 3 leads going at 480 volts going to your motor. So if we're telling this thing to run, and then this thing is going to have a 0 to 5 input. This is speed input. Here we get some run input. Here's a speed input. And so it says, okay, if you got 5 volts, so that means you want to go half speed. It's going to tell this VFD we want it to go half speed, and that motor goes at half speed. So, these are the kind of things you can kind of start putting together on your own as you learn this maze. And here's an automatic manual switch, and the automatic manual switch is for the speed. We can either put it in automatic, it's going to come right here from the computer. The computer's going to tell us what to do. Otherwise, if you put it manual, it's going to, there's that wiper, that speed pot. Imagine that. Where'd you guys see something like that before? Come back right here. This is a tachometer off to the right there. I don't know if we can get over there, but right here's a tachometer, and this gives you pulses. And this here is a little digital indicator that reads pulses and counts pulses and gives you an idea how much material is going through your bin and how fast it's going. Gives you an idea of what your speed is. And then you got this feed loss switch. If this thing here is open, it means that maybe the bin ran empty. If you go to the left there a little bit, David, thank you. A little bit more. There we go. If we get no signal back on TB 2-2, it's just say in your computer, it says, hey, you guys lost your feeder over there. Better do something. Okay. Why don't you go down there a little bit more for me, David, if you would. Maybe we'll run through the bins. And even if you don't have a BNS, your stuff looks pretty much the same, just like what you've been studying. So if you go over to the bottom, looks like now at the bottom there, they tell you things like your tachometer's got different connectors, and this is how you're going to have to wire them up accordingly. Looks like if you take a look to the left, it's got a 12-volt power supply in it, and that goes up there and feeds out 12 volts a bunch of different places. And so It's fumes, you're putting 120 volts in one side and 0 on the other, and then up the output's gonna be, it's like a battery charger. Okay,
Clarence?
can you, if you don't have any comments on that, anybody?
Yes, I
David,
do, Clarence.
go
If
for
you
it.
point out, put your indicator over one of the shield sections, and note that normally the shields on the wires, that's your signal wires, they try to sync the high voltage signal if they're running parallel, that it doesn't pick up a stray signal. Try to sync it to an earth ground.
You're talking
Most
about the
of the
shield.
times, those wires are only connected on one end. They'll pass through the plugs and such as a separate pin, such as in the center, you can see terminal 549 is connected on both sides, and it's also connected onto common. In other words, it's syncing at number 6 in that 1336 drive, that inverter drive. But you have to watch out that the length of cable quite often only gets shielded, tied in on one end. Otherwise, you're going to cause yourself problems when you go to track stuff.
That's important to do. With the scales we do, we and the shielded wire. What we do is just shielded there at the indicator, and then goes to the plug on its own. And then it goes to a shield terminal, but you don't ground it at that far end. Anyhow, that's a good point. Thank you.
Also, thermocouples, same way.
Okay, David, you want to see if we can let's see what else we can come up with on that same batch. See what the hell this one is. Okay, easy blend. Yeah, that's a good one. Here we're going to have some belt scales. Here we're going to have some asphalt meters. This one even has an output there to shut down your burner. That probably tells us to shut down the burner if there's no aggregate going in. Maybe. Damn, it's just exhaust fan. This looks like a burner control as well. Or maybe just the start stops. So this is start stop board basically is what this is.
Yeah.
And it's doing all the interlocking in between. On the left side basically is the inputs. We're seeing some things like transformers that will tell us what the amperage are. These are those donut looking things that the cables go through. And that's what you see where it says IXFMR. That's a current transformer. Sends a millivolt signal input. You can see millivolt. And so you got to find out what kind of millivolts we're looking at. You see if one of those things are working or not for you. So that's what's happening on the left. And then what's happening on the right, these are some modules. These are probably yellow ones, or yeah, they are yellow ones. So these are input ones here. So you can see once it's air pressure, you can slide a little bit more to the left there, David. That'd be good.
That's as far left. Oh, you're talking about right.
So right there. This is the output side. Well, actually, the input output. The yellow ones, you can see the top 3 ones are yellow. One of those things tell us about our air pressure. If the air pressure gets too low, go to your load out, it says, hey, maybe we ought to shut this thing down. That's what that one there says for where it says to load out system. The one above that, start, stop, control, automatic mode, something else, bunch of silos. It's the other yellow. So those are inputs, those are switches. And then if you go down to the black, which, oh, okay, this one that says black. And it goes out to some damn place, L1 filtered. Not sure what that means. Let's go to the next black one below there. That one says burner stop. It looks like you have to have 120 volts there to say stop that burner. And that means that it's going to put 120 volts across that CR coil. And that's the coil of the relay. And you can see the contact. And that shows a single pole double throw. That means there's one pole and then you either can go in one direction or the other. And right now it says, okay, I am normally closed. That's a normally closed set of contact. And then when you energize that, it's going to open it up and it will open up the burner control circuit. That's what that one's for. You got some outputs below the black one. The horn's supposed to go out for air. There's another siren also. If your siren's not working, well, maybe automatically, that's where you maybe go take a look at. These are the kind of things that can be, by looking at your drawings, brings you up to speed on stuff. And you know where to do some troubleshooting much quicker.
Clarence?
Yes.
I believe that burner interlock is your exhaust fan running interlock,
Okay.
because you're telling that VFD to run and the burner needs to know that the fan is started. And if Dave could slide to the left, there was one note down there off the CTs I think is kind of important. It mentions on the CTs what gauge wire right there. You see that notation for how many feet away you're running from your MCC cabinet to that little contact that you're reading in, what size wire you should be using to make sure that you're not getting any voltage drop on the wire and you're getting a true reading off your
Gotta be
CT meter.
kidding me.
Okay. You can see on the left there, they got some millivolt input there. I'm not sure if we got, if we're missing some, go up a little bit, straight up from there, David. Okay, yeah, basically that's current transformer input kind of thing. On the other side there was your IO, with the yellow stuff that was input. And then there's the output there, telling things to come on and off. And there's one that says plant start. You can see right there at the near the bottom right. It says it's a black one. This is okay. We're gonna start the plant. So the button control says, okay, we're ready to start the plant. So it's gonna send a button in to start up all things automatically, typically, through the IO system of the start stop control we saw before.
Notice on your black modules where the little fuse is showing between like TB2-9 and the output module itself, you notice the little F5 fuse right there? That's those little ones we were talking look like a resistor the other day.
Okay, F5 is fuse 5, F4 is fuse 4, F3 is fuse 3. That's a good point. So those are those little things that if, as Steve just said, if it's not working, you can do the module, but also check the fuse. Okay, this is the start stop board. Okay, David, see if you can find us the blending control board.
They're not labeled other than just numbers.
Just take a shot at it. We'll keep it on.
Blend interface rack.
Yeah, it's got the air cannon, so that's the blending board probably for wrap.
Okay, yeah, it's just start stop. We're looking for okay.
Speed control maybe for the feeders.
Right side.
Whatever the side's the biggest hole.
Yeah, well, anyway, the biggest hole is
You want me to keep searching?
Yeah, keep searching.
Bracket.
bracket.
That's the side the washer's gonna have to go on because that's a three.
Well, I told him I could put one on each side.
Okay.
I know. But he said that
Keep
on
searching until it says it.
some of the
You don't
brackets,
hear
you
it
can
start stop.
see where they tack the fucking head and the pole on like that.
That's the start stop. Maybe go to the bottom of all those lists you got.
There's a lot.
Okay, that's for warmer. There we go. That's what I'm looking for. Take me to the top. Okay, so anyhow, we got a power coming. Come on down there from that a little bit. So this is War Mix asphalt. So they actually do stuff with water turning on and off. That seemed like a phase that's kind of by the side. Let's go down a little bit more there, David. Thank you. So now we're doing some impact plus. What do we typical water egg starter selector? What are we controlling here? Go down a little bit more. This is a post sim board. So it's a sim. Yeah, this thing here is probably just for doing water that they had to add. It says, oh, you want to do some water on your. So this probably is. So go to the top of this if you would. They call it easy
It
flow
says
wave.
latex line there.
What's that?
One was, the last one was latex line. This one on the bottom is L1 when collector is running and computer okay. The notes about center of the screen clearance. Drop back down to where you were before, Dave, if you can. A little further.
This is the
Okay.
bottom.
There, the last one you had was latex run and dust run. See what I mean by where it says latex run for that controller?
Okay.
Oh, yeah.
And the drop down, I think your next one's the dust control.
Run.
Lime on that one. Yeah, and then dust run on this one. So they're interlocked in there. If you follow across where it says dust run, that the L1, when the collector is running, that's going to give power to that circuit. As you might have a manual override on it, but it is typically interlocked. So if it sees the collector running, virgin feed, it's then going to allow that portion there to run.
Okay, dokie. David, see if you look back at a few other ones. We're looking for the asphalt meters that I'm looking for and belt scales. It's called the blending control part of it. Right.
Dust.
Okay. Well, let's talk about this one here a little bit. Here's a dust surge bin. And this is for a way pot. And here's your blower. And they get a valve on top. That might be this guy right here. Electric, that's gonna open and close that valve. That says we're getting a signal here. And this is a automatic manual. And here, if you put it manual, you hit the fill pod. And then that will open up the solenoid. And consequently, everything that's inside of this silo right here is going to start dumping into here. Here's some load cells right here sensing that this is getting heavier. This is a rotary valve here that's going to empty it. And this rotary valve here's got to have some kind of a speed control to it. And here you can see a motor going to that rotary valve. And from that point here, it says, okay, here's my, now this is for a DC motor right here, because it's got a field voltage and an armature voltage. And the field voltage is going to be there all the time, and the armature voltage is going to change. And then it comes with this, and so this Bronco is a DC motor control, just like we've been troubleshooting. So this is the A1, A2, that off of that there. So now we said it takes three things to make this run. Well, we got to have power to it. we gotta have the speed signal, and we gotta have the stop start signal. And so the stop start signal might be the stop start signal could be right here. It says we're gonna apply the power the same time as we tell this thing to turn on in the first place. So the fact that it's got power there or not, so it means that they're asking for it to be there all the time. So this basically needs just two signals to it. One is power. It just gives power when it needs it, and the other is it's the speed signal, and whatever the speed signal is set up. And if you look at this, oh, there's a manual thing right there, a speed bot. Did we ever see one of those before? And turn what's in
David?
between there, and we troubleshot that.
Can you zoom in a little bit more? Because Clarence, you're right on that being power through that relay, but if you go down here to terminal board 2.8, terminal board 2.7, that's probably the run signal. And then terminal board 2-3, 2-1, and 2-9, it'd be your forward reverse part of the circuit. And there's just standard jumpers in there. So that nobody can come in and change it from going from forward. And anytime you give it power on your L1 and L2, it has permission to run. There are some cases where you will keep your L1, L2 power on and not be switched. And that same Bronco 11 controller will then work with a permission switch to run between like terminal 7 and terminal 8.
Depends on how you program. You got so many options. The world is your oyster, isn't it, Steve?
And the
It's
most
like-
important thing in this case is RTFM, guys. And that's read the foolish manual. You may substitute words appropriately.
Okay. If you guys get smart enough, you're like Burger King. You can have it your way. Okay. So this here, I'm still looking for right now. What the hell are we looking at here? Oh, so this is a waypod thing. Okay, what else we got on this besides waypod stuff? But
If we flip down this blending board, we might have asphalt on the same sheet, Clarence.
okay, do it. Looks like water.
Water, mineral filler.
Okay, next sheet, Dave. Now, guys, if you've got sheets like this naming label in here, you can go in and usually rename it in your program. So you know that sheet blah, blah, whatever number is your blending, is your cold feeds, whatever, and will help when you're searching for them like this. But that number, if you give that to whoever is helping you troubleshoot would be able to pull up the same sheet then. So you're both working off the same print.
Yeah, not that one, David. It's okay. We're going hunting through this.
Pulse board, that's baghouse then. Variable drag slot.
They did a variable drag sled,
Optional.
huh? That's playing with fire.
Have we tried that 3A one?
No, we'll have these guys.
working.
We'll have these guys take a break after we find this, and then here he is. You got it.
This is it, I think, because you got an AC temperature input. So that's got to be your asphalt blending.
Okay. Mixed over a couple AC. Come on down there a little bit, David. Okay. Here's our divert solenoid. Then look at the divert valve, and that's got a little limit switch tied to the back to that. Bet you that little yellow limit switch goes to a yellow block, telling you that we're actually closed. Black one to the solenoid at there, 2B2-16. This guy right here. This is That's gonna come from a black block and say, okay, open that thing up. And then the valve opened up, move that switch goes back and it's on to the yellow one, the yellow one's its red light comes on and it says, okay, that one switch. So that's what you're looking at. I mean, when it comes to troubleshooting, it's just not, this has just made it that much easier for you. So this is a step in the right direction. It's up to you guys to keep after it. To play around, be curious. Don't be stupid though. We taught you how to not to be stupid. There's your asphalt pump that goes to a VFD. It's got your run, there's a reverse switch there on that one VFD there. And oh, you want to start? Okay, do that. Oh, you want to go reverse? Do that. So that's programmed right in the VFD whenever you got certain terminals being jumpered out. And then you got your speed saver. You saw that before. That's not a big deal. You got a tachometer that says, okay, we told it to go the speed, but is it really going that speed? And it comes back and tells you if you're going that speed or not. And, okay, let's see, this is what looking for out test. So that's my story. I'm sticking to it. I'd say it's time for a break. And Steve, if you want to show them some stuff from here, that's fine by me.
All right, when you guys come back in from break, have some questions ready, please.
Okay, it's about 2:15. It's 2:03 now. Maybe if you want to come back at 2:15, then it's all down here from there.
All right.
Share it up here. Nope, not that one. Wrong one, guys. Let's go for the other one of these.
I was a couple minutes late back. The electrician was actually showing me they're rewiring everything. He was actually showing me how the DC motors worked and stuff
Excellent.
inside the electrical room.
Okay, did that share come up that I started on or no?
I don't see it.
Okay. Well, let me hop back over here, stop that one. Come back in here and share screen again. Windows, there we go. Okay, we see where we got the wall plug on that drawing? That look familiar to you guys? Okay, this is kind of the same drawing that Clarence had with that open and close switch and such. The top part was that drawing he had here. Let's turn on the power. Oh, I got a short circuit someplace. We'll have to go find out where that is. Yes, let's isolate that. Where we get the short. Oh, that's why. Well, we'll ignore that for now and just get back to it. We'll take and eliminate one wire quick just to see if that'll do it. Well, shoot, we'll turn off the power and I've got a problem on this one. I'll have to troubleshoot in a bit. But this is kind of the same circuit that Clarence had with the photohelic and such on it. We had the manual switch and the automatic switch all are combined. You've got one operator up here. And you see the two contacts down below it in blue?
Yep.
And depending which position that switch is whether the contact's made or not. They usually use like X's and O's. X means it's made in a line and O means it's not made. Similar to this on-off one right here. You see where I've got the contact configuration up right now? We've got 3 positions to the switch. In the first position, 6 to 3 is only on in position 3. Position 2, neither of them's on. In position 1, only the bottom one is on. In position, okay? So the next one I want to go on is going a little bit further over here to the right-hand side, where we've got the wiper for the control motor is out in the actuator on the damper motor. You've got an open motor and a closed motor out there that's trying to drive the damper clockwise and counterclockwise. Everything in that dashed area is actually connected to the actuator itself. Well, that wiper, if we come down here, think that wiper is just a potentiometer. It's the slide wire in the damper, and it's hooked up to that little power supply that Clarence was telling you about. And it's sending the volts out through that wiper and then reading it back in to the voltmeter. The photohelic is right here in the middle. It has the high and low pressure switches. It's got 110 on it because the signal coming in from the outside is a little air pressure signal that's driving the little damper or the little oil cans here, the pressure in them to make them go ding ding and either make or break. And everything in that solid line there is in that box. These little oil cans are set points that you're going to move with red needles on those little black knobs. So, any other questions on that part of it?
Looking good, impressive. I like it.
Nathan, you got any other questions on a DC controller or such that you were wondering about? Or the electrician get most of those answered for you?
The electrician answered quite a bit of it.
It's important that you get his number for later on so that he can help explain stuff later on when you're working on it. And
All right.
congratulations for asking questions. That's what we're trying to get across to you guys is we don't know everything. The local people that work on it most often have the answers. Ask.
And then he was showing me the newer well, we have the older heater
The old feeder controls and the new feeder controls are different.
yes.
Okay. What brand are the new feeder controls?
I'm not sure. I didn't see what the brand was, but I know we're still using some of the old heaters.
That makes sense. They're keeping probably the same controls on the asphalt, maybe on the wrap. If they only changed the virgin cold feed, you just change those because they could have quite likely have come with the bends themselves.
And he was showing me how the auxiliaries and stuff worked as well.
Good, good. Jesus, you think of some good questions?
No, I don't got anything at the moment.
Oh, so 30 seconds from now, after we go to the next guy, that's when the questions will come.
Yeah, most likely.
Well, if they do, ask. Isaac, how about you? We got you squared away or we got you totally fucking confused?
No, you guys have helped out a lot, especially getting kind of the baseline and well, even past the baseline, all this stuff. I think it's more so just getting into our own plants now, or and figuring out where everything is as far as our plant.
Now, guys, be careful. I'll tell you another one of the big secrets. RTFM. And that stands for Jesus.
Hold on. I lost you guys.
What's RTFM stand for?
RTFM. Read the freaking manual.
Okay. Now, there's another little thing you guys should remember out of this workshop. And it's going to be a hard one to forget. Plant go down, phone go up. Jeremy, you're snickering. Why is this?
I've had to explain to several paving bosses and superintendents that I can't talk on the phone and fix the problem at the same time. So they're going to have to buy me. When I tell them 15, 20 minutes, I'll call them back. They give me 15, 20 minutes before I call them back.
Yep.
Hmm.
Now, you guys might want to take and make yourself an emergency contact list. Yeah, you're going to have the fire department, the owner, and the hospital on part of it. But then you need to put down, who do I call if I've got a blending control problem? Who do I call if I need to wave off that tanker? Who do I call if I'm all of a sudden short on fuel oil? Whatever. Put the contacts down that you need. Make your own little private phone book or tack the thing up to the wall where everybody's got access to it. Those numbers, when you're in panic mode, come in handy. Panic mode may be determined by the day and the hour. Clarence, you got anything else to add here?
Okay, I don't. David, are you there? David is there.
Yes.
We're at the end of the troubleshooting part. There's some of the skill we call expert, but and we're not going to go through that per se. But David, I'm going to ask him to go through that quickly. You guys will give you a bit more of to pick up on some things about the terms and what kind of things you can do, et cetera, et cetera. Other than that, I've got my main thing that I want to make sure you guys understood was the troubleshooting part of it. And that, first of all, you can do it safely, keeps you out of trouble, so you can do the maintenance on your plant correctly. And then the other thing is that you can do that if someone gives you a call and says, give me a reading about something, what kind of voltage do I got and when, if you know how to do that correctly, get that back to them. There's a lot of phone troubleshooting you can get done. You can be more of an electrical person and do more troubleshooting on your own. And so this helps you do that. So it gets you put in that direction. We're not out there. We're just trying to help you to maintain your equipment safely and things like that. So basically, you have performed everything I wanted you to do. We got some certificates that we're going to give you at the end of the, that we're going to be mailing out to you, but at least you'll get to see them. And I thank you for being here. But here's some troubleshooting advanced stuff right here. David's just going to push the button and let it run. If anybody has a question, just go ahead, stop. There might be some questions there, go for it, but let's take it from there. David, let her buck.
Are you wanting to like speed through this though, or how are you wanting to do this?
Do I want to do what?
Are you wanting to like speed through this, or how? There's a lot here that we just did.
Okay. Well, if you just let it play, so this is 41 minutes.
If I let it play, we got about 3 hours worth of troubleshooting.
Okay, well, I would say at least just do the troubleshooting advance, and that's all we need to do. How many modules of troubleshooting advance do we have?
5.
5 of them?
Yeah, that's about 220, probably something like that.
Okay. Well, let's go through a couple there. They got some stuff in their book that they can that they can see and review on their own. But I'd say that, we don't want to wear these guys out. We want them to remember what we want. Too much information, sometimes it's too much information. So I would say at least do this module right here. And then after that, we'll probably give you guys your certificates. Is that a good way to do it, David?
Or we just kind of skim through these and hit some of the questions again, or
Okay, do it. Skim.
Guys, if you see something that makes you curious or causes problems, yell, and that's the sections we'll try and answer questions on, okay? Probably speed 1.25, Dave. Or yeah,
I think I'm
going
just gonna
through
try
like-
and hit some hot points here and
sounds good.
The open winding burnt open. What are the symptoms when actuating the open close switch?
Okay, David, pick somebody.
all right, Isaac. The open winding under damper drive burnt open. So what are gonna be the symptoms when we try and open or close? Will the open light illuminate? You're muted. Will this light come on if we try and open it?
Oh, let's see, open one burnt out. Open winding burnt out, burnt open. I would say yes, since it's burnt open, right?
This part's burnt open right here.
Okay. Okay, so
Between
you're,
2 and L2 in that drive motor.
oh, okay,
So is
okay,
the
so
light above it, the green light, you go on
it would come on, yep.
if you move your manual switch? Okay. Now then, will your closed light, the red light, go on?
The closed light will not go on
Why not?
because we're in manual, correct?
We're a manual. Now, if I say I switch over to close, the light should come on, right?
Correct.
Okay. Position indicator does not move, but the closed actuator will move open. That sounds backwards, so I don't know if that would happen. Drive motor does not open, but it will close. Well, if we get power into 21, power to 3, through to L2, we know it'll go close. But we can't open it. So I'd say A, B, and C. I mean, A, B, and D.
A, B, and D?
Yep.
Okay.
The correct answers are A, the open light will illuminate, B, the closed light will illuminate, and D, the drive motor does not open but will close. How does one troubleshoot the burnt open coil problem when checking for voltage at terminal 2? Choose all that apply.
All right, Nathan. So we have the burnt open coil on our damper drive. And we're gonna do voltage checks at terminal 2. So are we gonna check in manual, check for voltage when opening the open switch or actuating the open switch?
I think that's the correct answer.
That's one of the correct answers, at least. So what would you expect to read on number 2 if you take the switch and move it to the open position?
And it's burnt out right there.
Between 2 and L2, it's burnt out. But you've got your probe on terminal 20. So do you
Right.
expect to see a voltage?
Yes.
What do you expect to see?
120.
Okay. In automatic, should we check for voltage when setting the lower set point below the indicated pressure? That good to do anything for us?
No.
Okay, in automatic, check for voltage when the setting the lower set point above the indicated pressure. Yeah.
Yeah.
Okay. Let's see what they say, Dave.
The correct answers are A, in manual, check for voltage when actuating the open switch, and C, in automatic, check for voltage when setting the lower set point above the indicated pressure. Wire is disconnected from actuator terminal 3. What are the symptoms when actuating the open-close switch?
Jesus? What do you think? This is actuator terminal 3 right here.
Okay, and then from 21 to 3, it got separated or disconnected.
Yep.
That sounds like it. So will the open light go on if I'm moving the manual switch?
Yes, the open light should still illuminate.
How about the closed light?
Yes.
Yes, that should
Okay.
illuminate. It will not close. The answer would be C.
All right, so we're gonna go A, B, D.
Why is this no? Yeah, A, B, or D.
The correct answers are A, the open light will illuminate, B, the closed light will illuminate, and D, the drive motor does not close but will open. The contacts of the close switch won't close when actuated. What are the symptoms when actuating the open-close switch?
Isaac, what do you think?
Contacts of the closed switch won't close when actuated. The symptoms. Okay, so the open light will illuminate. Closed light will illuminate.
So this is the open close switch right here.
Okay.
The manual switch.
Okay, so it won't close. Okay, so it won't close, so it's not letting anything through.
Right. So this XOO is our close side. So this is where, when you press close, this is where it should be coming through. But we're saying these contacts never close.
Okay.
So is my light gonna go on for close?
No.
Okay.
No, because you have no power over there.
All right. Now the position indicator does not move close, but it will move open. True or false?
I'd say that'd be true.
Okay. Drive motor does not open, but will close. True or false?
Say false.
I agree. So we're ABC.
The correct
Oh, that's
answers
right. B doesn't
are
light.
A, the open light will illuminate, and C, the position indicator does not move closed but will move open. White wire number 2 falls off of the L2 terminal of the photohelic. The manual mode works correctly. When in the automatic mode, no matter where the two set points are set, choose all that are true.
All right, Nathan.
It's kind of hard to see. Oh, there, it cleared up. It got blurry for a second.
All right, we're counting on working through the photohelic now. Now,
Okay.
if you're not touching the manual button and the photohelic has not got power to L2, do we expect the switches to move to show us the open light or the closed light?
No.
Okay. Position indicator does not move closed, but moves open. True or false?
I'd say false.
Okay, how D? Drive motor does not open, but will close. True or false?
False.
That one's okay. Now, sometimes on those drive motors, because the switches have to have the electricity to work, they can't work then. If they were a mechanical switch and we're actually determined to wait on the pressure, then they might. But because it's a photohelic switch, it's counting on a little beam of light inside the deal to work off that pressure switch. They're about the true definition of a magical box, black box or whatever, because you're taking a pneumatic signal into, making it into light, and then using that light to flip a mechanical switch. So without the electricity to make that mechanical motion in the light, ain't nothing working.
Well, I think what happens is that, so this is normally closed and there's 120 here when you're in auto. So that's going to be shooting right through because the switch isn't going to change states. So that normally closed contact is
will
going to
go directly to open. I'll agree, Dave.
Yep. So you're gonna always have power to your
So
open
C
side.
is correct.
The correct answers
Yep.
are A, the open light will illuminate, and C, the position indicator does not move closed, but moves open.
Helic is actually an electronically operated pressure switch and will only actuate its contacts when 120 volts AC is available to.
No matter where the wiper is positioned on the slide wire, the panel meter and the test meter both read 12 volts DC. Choose all that apply.
Jesus, what do you think?
Dave, can you run it ahead just a little bit to get rid of the pause box?
Yes.
No matter where the wiper's position on the slide wire. Bam.
Excellent.
So we have a 12 volt power supply. And we're expecting that 12 volts to change as we're checking the wiper as we change the pot position. But our panel meter isn't changing. It's just reading 12 volts all the time. If you turn your pot all the way down, it still reads 12 volts. So what do you think would cause that? Do you think the wire between terminal 4 and the panel meter is broken? I think that would cause it to go to 12 volts all the time. This is our positive terminal. This is our negative.
Okay. So
This is our number 4 is our wiper. So this should be proportioning based on where we have our dial set at. If it was at half speed of our 12 volt supply, we would expect this to be at 6 volts, right?
correct, yeah.
All right, we're normally expecting that little wiper thing to have power on the right-hand side of it. It's going to be plus there and negative to the right. That's supposed to be what it's doing and taking the partial signal off down to terminal 4. But this time we've got our meter set up so our meter is tied in. The negative goes to terminal 2. The power comes in off of 1 to 7 like it's supposed to. The power is supposed to go across that horseshoe portion, but it's actually coming out terminal 4 on the meter. We're reading our 12 volts there on the meter. So what would be missing to keep it from getting back to 2? Would it be wire 9 to 2? Or would it be wire 8 to 9? Or terminal 7 to 1? Well, we know 7 to 1's working, right?
Uh-huh.
So that's not broken. So what do we think it is? Do we think it could be? If we don't have the wire 8 to 9, what happens? It has to find another way back to the power supply, right?
Yeah. Okay. So 8 to 9, I guess, is possibly broken, so it's finding its way back through 4 to 2.
And now another reason I say that, because it looks like the meter's getting the full 12 volts also. It's all the way over to 100% open. And you see the other side of the meter goes back and uses wire 2 to 9, so we know that wire is probably pretty good. Otherwise, the meter wouldn't say squat. So that leaves us with what?
That'd leave us with just the actuator mount slide.
Leaves us with number C. Now, what we're trying to do in this is teaching you guys how to break it down actually. Cut the thing up into manageable sizes to look at. We know in this case that we've got power between 1 and 7 because the meter's telling us we've got power that far. We know that power is also going through this damper position meter, the full 12 volts, because it's reading 100%. So that means wire 2 to 9 is okay. That leaves us with 9 to 2 being broken. Nope, that's not it. Wire between terminal 4 and the panel meter is broken. Nope, that's working because it's got full voltage there. So that only leaves the wire between terminal 8 and 9 is broken for an answer.
Okay.
That's how I arrived, and you arrived at that answer. So you want to hit go, Dave, and see if I'm right or if I'm clear off
Choose
in
let
the
apply.
woods again.
The correct answer is C. The wire between terminal 8 and terminal 9 is broken.
No matter where the wiper is positioned on the slide wire, panel meter and the test meter both read 12 volts DC. The only causes for that would be the wire between terminal 8 and 9 is broken, or the wire between terminal 8 and the pot 8 is broken. Notice the current flow from the high pressure side of the power supply through the advances in electronics have made the variable frequency drive, VFD, inverter economical, practical, and reliable when applied correctly. These electronic advances not only improved the reliability, these advances also allowed the VFD
of 25%.
We didn't really cover any of this scale troubleshooting stuff. Maybe we should be watching this section.
Scales we covered back a week ago, remember, Dave?
Yeah, but not like the spanning stuff, really. I don't think that we didn't get into spanning stuff like this, did we?
Yeah, we did.
We did?
Yep.
Okay.
Told them how to adjust.
Okay.
Basically, remember what we were teaching is the first thing to do is make sure it's repeatable so that you can actually span it. Because if it won't repeat, be it the belt scale, the dust scale, or the asphalt scale, you're never going to get it adjusted.
Yeah.
Jeremy, you got words of wisdom on scales?
You just said it right there. If it's not repeatable, you can't do nothing with it. Doesn't matter if you're minus 10% or plus 10%. If it's repeatable at either one of those, you can span it and get it to be right on the money that way. But if it's not repeatable, if it's bouncing from 2% minus to 4% positive back to 2% back and forth all over the place, jumping around. There's nothing you can do. You got to figure out mechanically or where your issue is before you can try to span something of that out of the
Now,
equation.
one other very important part in making certain the scale is repeatable, make certain your reference scale is repeatable and certified. So that if you're trying to work to a scale that's 5 tons off all the time, well, you're going to transfer that error immediately over to yours. You have to make sure whatever you're going to reference or use as a reference is good. You know, trying to make sure they've gotten a scale sticker on if you're using a local truck scale or something lately. One of the strangest ones I've ever had was we had a plant that was set up, closest scale was 50 miles away. So we took and we loaded our 3 dump trucks up, high, medium, and low, sent them off, driving their 50 miles. Before they weighed the truck, we had them take and fill the fuel tank, weigh the truck. They went over a quarter mile and dumped the load because the guys were going to be stockpiling material there anyway, so it wasn't a wasted haul. As soon as they dumped the load, they come back and got their tare weight. They then phone called and gave me all 3 sets of readings for all 3 trucks. And whilst they were driving their hour back, we got the plant ready for the next run. We made an adjustment if we deemed an adjustment was necessary, and then sent the next round out. And remember, as soon as you get the proper answer, you want to run one more test to prove it's repeatable, to prove it's right, and it wasn't a fluke that you saw. Now, when we were on the dust, the main problem with the dust is make sure your dust, baghouse dust, cement in the silo, whatever, is a repeatable dust that's going to be the same number of pounds per cubic feet. If you've got one of the newer scales, such as Dave makes with Clarence, those are measuring off of impact and gravity, not volume. If you're using a vane feeder, that's a volumetric scale that needs to have a consistent volume to give a consistent answer. Jeremy?
Yep. And making sure your truck driver's not getting fuel in between. I had that happen before. He went and topped off with fuel and then didn't tell nobody. And I'm like, what took you so long? Oh, I got fuel. I'm like, did you get a new tare weight? No.
Also, is the truck driver in the truck or out of the truck? You can't do one load one way and one load the other way.
Yeah.
Because most truck drivers, that's 6, 7 scale grads at least.
Yep. And just like you want repeatability on your scale, you want the driver to be repeating the same way he's doing it each time, just to be more consistent of what you're looking for, consistency.
And that even includes pulling onto the scale the same direction and trying to park in about the same direction on the scale.
Yep.
We found out one case where we knew the scale was bad because the truck driver, we finally took the truck, pulled on one way, pulled them off, turned them back around, and we had 2 tons difference in the scale weight.
Yeah.
That's when we got the scale boys out to get the reference scale fixed so that we can calibrate the plant.
And I always used a pickup or something, no matter whose scale I was using, even if the sticker was pretty recent, I'd pull my pickup on each end and check it a couple of different ways before I trusted that scale, just to verify that it was at least reading my pickup the same weight all the way across.
The other thing is if you're to a small graduation that you want to try and get, you're trying to get like 10 pounds or so and you're on a 20-pound platform scale, and you need to know where you're at in that 20-pound changeover. Are you within 10 pounds of it, or are you just after it? Take yourself a small weight. If it's a 20-pound scale, probably a 10-pound and a 5-pound. It can be a gallon jug of water or 2 gallon jugs of water. Set them on and off and see if that is enough to change the weight on the truck. It'll let you know a little bit closer if you're really having a pain getting it in at a low tonnage or something. that'll let you know on your break point there that you might be able to understand your numbers a little bit tighter. So. Other
And I always
tricks
try to
you-
go with the bigger the number you can calibrate to, the better off you are too. Like the 10 plus tons is better than 5 tons trying to calibrate a belt scale. The bigger the number you can get each time's the better reference. Because if you're
if you've got a
calibrating your
two-
scale and
if
you
you-
calibrate it 100 pounds and you're off at 100 pounds, if you're 2% off at 100 pounds, that 2% is going to stay there when you're at 1,000 pounds. So the bigger the number, the bigger that your percent off is going to be. Like if you're 100 pounds off at the lower weight, you might be 600 pounds off at the higher weight. So the higher you can get that number, the more clarity you'll have as well.
If your asphalt check scale will hold 2,000 gallons, use 2,000 gallons if at all possible. Just don't use 250 because that was a convenient number and matched the time factor.
Yep.
Try to use the maximum amount you reliably can. Dave, anything on dust that you've worked at that they might be of additional help to these guys?
No, not really.
Anything on cleaning?
Anything on what?
Pivot points and such? Anything extra cleanliness they need to check on those?
In the scales, you mean?
Yeah.
Yeah, I mean, yeah, buildup's always an issue. Like with flow scales, impact scales, buildup's going to be an issue. So if you're having any moisture problems, that's going to cause you problems in your scale. There we
What
deal with
type of
venting
asphalt?
sometimes in dust systems. So if you're blowing the material, we always recommend venting. Some people don't think there's pressure that comes up out of the airlock below it, but some people do think there is. And we're one of those people. As materials going down the veins, air is coming back up the return veins. So pressurizing your scale is going to affect your scale reading. And it can also blow material out into your J box, and now you're getting filled up under your rounding load cell. So those are kind of issues people don't see until they become issues.
When it comes to verifying a scale on liquids, make certain you have a temperature if you're temperature compensated. Some scales are not. Some scales are direct reading on mass. Also, if the scale that you've got's got a entry for viscosity, enter that in, because the viscosity on the asphalts do vary. You need to make sure you're actually weighing what you think you're weighing. You want to skate on ahead then, Dave?
Yeah, there's a question right here.
Calibration checks at 3 different feed rates of 25%, 62%, and 100% of scale capacity were performed. The error percentages were out of tolerance, and the scale indicator should be respanned. The flow scale span was too high by 0.5% at 25%, 0.7% at 62%, and 0.9% at 100% flow rate. What span adjustment is necessary to bring the error band within the target band?
What do you think, Isaac? What adjustment would get all 3 of these points into this blue area? So this blue is what's acceptable. We can be plus or minus 0.5%. And our first test was 0.5% up, too high, and then it was 0.7%. So if we were using 100 pounds, we were looking for 100 pounds, we got 105, and then we got 107 at 313 tons an hour, and then we got 109 at 500 tons an hour.
I'd reduce span by 7%, 0.7%.
Boom, and then that would put all of them into the blue. I agree.
The correct answer is D. Reduce the span by 0.7%.
These problems, doing the easy checks first is important. Doing only the checks.
Continuous weighing is much more difficult to confirm scale accuracy when processing material through it than batch weighing. Cross-checking instantaneously and over time is an important tool. Choose all the applicable tools that may apply.
What do you think, Nathan? You think A would be a good one to compare, to confirm your accuracy?
I think A, B, and C.
I don't know that we need to check the density every hour. I'm not sure that that's a feasible one.
That might work if you're on just dust, where you're counting on a volumetric measure against a rotary input. Likewise, the temperature might be important if you're dealing with asphalt. It should be corrected automatically, but is it being?
Yeah, and temperature will affect your load cell as well. So if you start up and it's cold in the morning and then it's gonna, jump up 40 degrees throughout the day and the sun's beating on it, that is gonna change your zero. Let's see what we see.
The correct answers are A. Account for the batches of material already weighed and compare with flow scale totalizer, and C. Compare the speed, RPM, hertz, feet per minute, etc., of the variable speed device charging the scale with the flow scale rate indication.
Span number, DSP2. The exact span number is determined when calibrating the scale at production rates. If the
scale indicator provides 10 volts DC excitation to the load cell. The load cell has 2.5 pounds of weight applied to it. What is the load cell output signal? Choose all that apply.
What do you think, Jesus? So we got a 10-pound load cell with 2 millivolts per volt output. And we've got 10 volt excitation. So what that means is if you put 10 pounds of force on a 10-pound load cell, it's going to give you 2 millivolts for every volt. And at full output, it's going to put out the full 10 volts. So you would have 20 millivolts at full output, right? If you put 10 pounds of force onto this, it would give you the full output of 20 millivolts. Because you have 2 millivolts per volt, 10 volts. So 20 millivolts is your full output. So we're putting 2.5 pounds of force onto a 10-pound load cell. So what do you think we would get an output of if 20 is our max? You're muted.
Sorry. I would believe we'd get 5. That'd
5
double.
5 millivolts.
Yeah, I would double correct.
Do you think B would be?
You've got 1/4 of your 10 pounds, right?
Yes.
2.5 pounds plus 2.5 plus 2.5 plus 2.5 equals 10, right?
Yeah.
Okay, so if I've got 2 millivolts per volt, when everything's loaded up at 10, how much am I going to have if I have a quarter of that? Half of 10's what?
Half a 10's 5.
Half of 2 is,
2.5.
no, half of 2.
Oh, 1 point or 0.75.
No, half of 2
1.
is 1.
1. My bad.
What's half of 1?
0.5.
What's half of 1? Okay. And 0.005 is 1 or 5 thousandths of a millivolt, right?
It's 5,000ths of a volt. So this is actually the exact
Which
same.
is,
This is the difference between an auto ranging meter and a manual meter.
So 0.005 is the same as 5 millivolts.
These are the exact same reading.
Okay.
5,000ths
5
of
millionths
5
of a
millivolts.
volt.
Yeah. Okay.
But basically the easy way to understand this is that, so you push 10 pounds on this, you max it out, you get a 20 volt, you get a 20 millivolt output. But if you only do half of that, you're only putting 5 pounds onto it, you're going to get half of the output. So you're only going to get 10 millivolts output. Now we're going to cut it in half again to get to that 2.5 pounds. So we're going to cut that 10 in half. Now we're down to 5 millivolt output. That's a quarter of our full output. And we gave that load cell a quarter of its full range. Does that make sense? You're muted.
Yeah, I guess I'm just not understanding the question very well.
All right. Put it back in simple terms. We're going to go Canadian imperial gallons now. We got an imperial gallon, which is 10 pounds. We're going to take half of that jug. Half that jug goes going to weigh 5 pounds. Well, half of that half is a quarter. So it's going to weigh 2.5 pounds. That's how much weight we're putting on there. If the thing's all the way up there at 2 millivolts per volt times the 10 pounds, that's 20 millivolts. So half of the 20 is 10. And half of 10 is 5. Last I checked.
Yeah, I just where I'm getting confused is why are we going pretty much taking a fourth out of it?
Because we're only applying a fourth of the weight to it. This load cell only has 2.5 pounds on it, but it's a 10-pound load cell.
You couldn't drink a gallon of beer, but you could drink a quart.
Okay,
So we're measuring the quart.
Now it
Okay.
probably makes sense. That's what you're
Okay.
missing. This 2.5 pounds is what's applied to the total 10-pound load cell. If you do more than that, you're going to start damaging it. So at 10 pounds, it's maxed out. We put a quarter of the max weight on it.
Okay, I got it now.
So then we can figure out what the signal should be by taking a quarter of the full output.
Got it.
So we know what to expect when we take that measurement.
Okay.
Makes sense, though.
Okay.
Lost Nathan again.
The applied load to the load cell can be significantly more than the electrical output signal is indicating.
The flow scale is not properly vented, and processed material is venting into the load cell box. The load cell box is packing full. The load cell pinch point is filling in with material. The load cell is no longer free to move in the pinching direction when more weight is being applied. How does the closed loop control react?
Isaac, what do you think?
I'm gonna go with C. The amount of processed material being added to the mix is too high.
It's the same exact thing that happens as if there's a rock underneath the weighbridge outside, holding it up. Same stuff, and you're right.
The correct answer is C. The amount of processed material being added to the mix is too high.
Caused by a plugged airlock vent line, as shown in these 4 pictures. Shutdown application requiring a thin probe.
Low voltage signals must be protected from electromagnetic interference that can corrupt.
What?
Back up if you can to that picture of the probes. 30 seconds or so there. Okay, guys, what the difference in these probes is that first one on top has got an extra chunk of 1/2-inch pipe, which is protecting the guts, which is kind of like that bottom probe. The bottom probe, if it's in airstream, is going to react much quicker because it doesn't have that extra 1/2-inch pipe to heat up. It's only got that 3/16 or 1/4-inch diameter tube to heat up and cool down. Now, when you're putting the probe into an airstream that's got dust in it to sandblast it, it's quite often very smart to put like a piece of angle iron ahead of the flow close to this probe just to block the sandblast and the particles away from it. Make sure that you go in the full depth of the probe, that you don't leave the bottom 1/2 inch out and exposed to being sandblasted, because it'll sandblast a hole through it just as quick as it will the whole probe. If you get caught out and you do lose a probe like that, if you can at least take the wires and twist them together nice and tight, if it's like a type J thermocouple, that will give you a reading. Don't leave it in there very long. Get the probe on as quick as you can. But you might be better off just sticking the wires in than actually trying to use a big heavy probe, because the reaction time is going to be that much slower. The other fun thing to know about wires is the red wire is always the plus wire. The white wire with type J is minus, or the yellow wire with the type K. Also notice on type J thermocouples that white wire is magnetic. If you've got a little magnet probe like on the end of one of those little baby screwdrivers, the white wire should suck to that because it's an iron Constantine wire. Okay.
Low voltage signals must be protected from electromagnetic interference that can corrupt the signal when transmitting over distances. The shield on shielded cables protects the signal from interference when properly grounded and prepared. Choose all that apply.
What do you think, Nathan? We're supposed to ground your shielded cable at one end only or at both ends?
I believe you do it at both ends.
No, one end only. One end only.
You're trying to drain the signal off. If you connect it on both ends, it sets up what they call a ground loop. Ground loops are extremely hard to find in the field.
Do you think you should be taping up the uninsulated ends of the cable?
No, I don't feel like that would protect it.
For the same reason you do want to, because that would ground it anywhere there's metal insulation around this. So that's connecting all the way through the cable. That drain wire is pulling the transients away. It's pulling in one direction. Well, for the same reason, you don't want it wired, you don't want it grounded at both ends. You don't want to have this insulation free if it's touching the cabinet or if it's touching a ground wire, anything that's grounded, now you have a ground there. So you do want to tape up these shield wires are usually bare wires. So it's not, you'll have several insulated, maybe it's just a pair of insulated wires and then you'll have one bare shield wire. You ground it on one end, but you want to tape up the other end to make sure that it doesn't accidentally ground. Even though you didn't ground it, you put it to a shield terminal.
You may not have intentionally grounded it, but it may have found a ground. That little extra wire you cut may be up against something to ground it out. And that's where you want to tape up. You want to tape up that little bit of extra wire on the end that doesn't go to a terminal. That way it can't help itself.
So the tape would be considered a ground if you taped it, so it
No,
would still be, it
No.
wouldn't?
tape is not a ground. Tape is an insulation. It's isolating the
Okay.
wire that you're wanting to protect from making a complete path. In other words, you cut the jacket back on the outside of the cable because you had to get the other two wires out. Well, then you trim back that shield wire and such as far as you could, but there's a little bit left and it's kind of fuzzy on the ends. That's where you want to get the tape on between the outer case of the cable and maybe a 1/4 inch past where those little frayed ends are.
Yeah.
You
Like
leave
this
your other
crosshatch
wires
stuff.
leave the other two wires sticking out so you can get them in the terminal or wherever you're headed to. But just that little fuzzy end is what you want to cover.
The correct answers are A, ground the cable shield drain wire at one end only, and C, tape up the uninsulated ends of the cable.
Listed pair or This module offers the opportunity to learn about the different types of control systems, their benefits and disadvantages, when they should be used, how to troubleshoot and fix them, and
Apply.
What do you think, Jesus? What is a closed loop control system? Is it a control system operating in automatic mode?
Closed loop is, yeah, I think so.
Okay. Does it respond automatically to changes in the process?
I don't think so.
I do think so. So a closed loop, an open loop control would not. An open loop control means you're just sending out a signal and you're expecting that to happen. You're not going to check up on it. Your supervisor's going to tell you to do something. He's not going to see if you actually did it. That's open loop control. But if I
Open
tell you
loop
to
is-
do something and then I come back and check with you and make sure that you did that by getting a signal back telling me that you did do that. I told you to go this speed and now I'm getting a signal back saying that you did go that speed.
Okay.
Or so if you're, so if there's a change in the process, I'm going to change my tons per hour. That's going to tell your oil to go, it's going to automatically control other things.
He says, think of it this way. You've got the switch on your photohelix set to manual. I've still got the signal coming in. The red lines are, like black needles moving back and forth. That back and forth is the feedback. That's the automatic. But unless I go to automatic, that signal is going to be all the way one way or the other, still waiting on the nut behind the knob to turn the knob, either increase, decrease, or automatic. So the closed loop in that case is you're getting the air signal back in to control the damper. The damper is being controlled hither or yon. I can control it all day long with my manual switch, but unless I do something with the signal that's coming back in, that's an open loop. You close the loop by putting it in auto.
Okay. Okay, so
It's like
A and C.
same on your asphalt. I can set the asphalt wherever I want to in manual. If the tonnage changes, it's wrong. But if I put in an automatic, the signal that it's sending back in as to how much the flow is will be automatically controlled and proportioned. So that is a closed loop system. You make a change, an answer is coming back in, and then depending what the answer is, the next change is made.
Okay. All right. Yeah, I'd have to go with A and C.
But also B, it automatically responds to changes in the process as well.
Oh, yeah. Yeah.
The correct answers are A, a control system operating in an automatic mode, B, responds automatically to changes in the process, and C, correct an output for any process changes in relation to a set point. Aggregate, the mix, process variable PV drops to 292, a wet slug of sand in the aggregate. Should the controller make major corrections to be done instantaneously or minor corrections over a period of time?
Nathan, what do you think?
I'd make minor corrections over a period of time.
I actually don't remember what this is going to say. Let's see what it says. Nice.
The correct answer is B. The controller should make minor corrections over a period of time. The burner control symptoms game. Closed loop control troubleshooting. Scenario. The burner control is set to automatic and controls smoothly until the following upset in the process happens. The waste oil burner fuel filter becomes clogged over a period of a few hours. The pressure gauges on each side are used to indicate how clean the fuel filter is. When the difference between the two readings increase, this indicates the filter is getting more plugged. The pressure differential is increasing. Based on this problem, what would you expect one of the symptoms to be?
Isaac, what do you think is going to happen here? Filter's clogging up over several hours.
Okay, so the burner actuator drives open slowly as indicated by the burner position indicator. The burner actuator drives open quickly. So it's not gonna, since it's happening over, it's not happening right away. It's gonna obviously move slower, but the actuator is gonna open up slowly. Definitely going to be a couple in here. The controller's hunting for its set point.
It's really not. So it's either open or close slowly, open or close quickly, or it's going to hunt excessively or slowly.
Okay, I would go with it's going to open up slowly over time as the filter's getting clogged.
Yep, nice.
You almost think they've been
Correct
listening,
answer is
Dave.
A. The burner.
What was that?
I said you almost think they've been listening well.
That's right.
Until the following upset in the process happens. A mixed temperature probe was used in place of a normally thin temperature probe. Based on this problem, what would you expect one of the symptoms to be?
Jesus, what do you think is going to happen if you use a thick, massive mixed temperature probe in place of a thin temperature probe?
The thick one's gonna take more time to realize it's getting more hot, so it'd be slow. It would be a slow indication.
So you think it's gonna drive open slowly, or think it's gonna drive close slowly? Do you think it's gonna hunt? Which would mean opening and closing. Hunting means that it's passing its set point. It's going too far, it's opening too much past the set point, and now it's gonna go past its low set point. It's just gonna keep moving because it can't find a spot in the middle.
Yeah, I'd say that one. It's
You
gonna
think it's
keep
gonna hunt
moving by the
slowly?
time it. Yeah, it'll keep moving slowly.
Nice
The
job.
correct answer is F. The controller is hunting for its set point by too slowly opening and closing the actuator.
The burner control is set to automatic.
Scenario. The burner control is set to automatic and controls smoothly until the following upset in the process happens. The temperature controller's sensitivity adjustment, its proportional band or gain, is set way too high. Based on this problem, what would you expect one of the symptoms to be?
What do you think, Nathan?
I actually can't see the answers. My screen's blurry.
So our controller sensitivity adjustment is set way too high. So do you think that's going to cause it to open or close quickly or slowly? Or do you think it's going to make it hunt, keep opening and closing?
I actually think it would close it pretty quick.
I agree with you, but I think it's going to do it so quickly that it's going to go farther than it wanted to. And now you went beyond your set point.
Right.
And so now it's going to do the opposite, right? Now it's going to start opening really quickly because the sensitivity is really high. Now you went past your high set point. Now you're going to go back closing again. So do you think it's going to be hunting really quickly?
Yes.
I do too.
Now, remember what I told you to fight this in case somebody comes in and adjust them? When things are operating correctly, record the readings. So that if for some reason you lose a meter and you have to change it, or somebody from the office comes in, it's going to really help you and changes and massage your settings, you can go back to what you had that was working, as long as you've got a written record of what it was.
Yeah.
So like since our actuator wasn't working correctly, it would it actually just, if you had that set too high, it would actually just high stack it.
And in a wet wash, that's hard to do.
Yeah. There's a few things from this class I've learned that there's a few things on our plant that we need to work on.
Well, glad you picked up something.
Yeah. Read this up and goes in.
The correct answer is E. The controller is hunting for its set point by too quickly opening and closing the actuator.
The burner control is set to automatic and controls smoothly.
Scenario. The burner control is set to automatic and controls smoothly until the following upset in the process happens. Cold, heavy waste oil was added to the fuel tank. The plant's inline heater to boost the temperature of the fuel going to the burner was not hooked up. Consequently, the added cold oil mixes with the heated oil and slowly brings the temperature of the oil down from 148 degrees to 88 degrees. Based on this problem, what would you expect one of the symptoms to be?
Isaac, what do you think?
I'm gonna say the actuator is gonna open up quickly to accommodate for that colder oil.
I think you really got to consider.
Oh,
How
slowly.
long did it take to put that load in? I mean, if you can dump that whole load in inside of 2 minutes, 8,000 gallons, yeah, then it'll be quick. But it's more likely to take them 15, 20 minutes to get that amount of oil transferred, right? So
That's-
how
yeah.
fast do you think it's going to react?
So I guess slowly. It's right in the, I guess I missed the slowly brings the temperature down too, but yeah.
Yeah, that's the operative.
No, I'm not too familiar with the automatic actuators. Ours is it's manual. There's no way to put it in automatic.
There may actually be on your little controller, there may be an automatic manual switch on that square controller.
What did you say, Steve?
That depends upon the control surface. All right, that controller that you've got, that little like blue box that says Honeywell or something,
Yes.
may have an automatic manual switch built into it.
Oh, okay.
That would be the automatic control in there that has to be set. And it may be not properly adjusted and set up to where you're just choosing to run it manually. Nothing
Oh,
wrong with
okay.
manual control. Quite often, a good, well-trained operator is a better controller than automatic because much the feed has been adjusted, where the poor burner's just reacting on, hey, the temperature goes out so and such. That's what you told me to be, right? What do you mean you put 50 more ton in ahead of me? And I got to heat that too. The smart operator knows he just did that change and could increase the fuel flow to make it hotter to match the tonnage coming in. Or if all of a sudden the belt stopped running, the operator knows there's no more material coming in. The burner only knows that, hey, what's going out the drum is 300 degrees. What do you mean there's no more in the drum? Until it falls out, it doesn't know the temperature. So in that way, a manual operator can beat an automatic control because the manual operator is using more information.
Right. And that's the way I was taught, is doing it manually here.
Nothing wrong with it. I mean, if you get some pictures later on, we can talk about it. Take some good, clear, close-up pictures of your burner control and such, and we can maybe walk through it.
Okay.
Okay?
The correct answer is A. The burner actuator drives open slowly as indicated by the burner position indicator. Scenario: the burner control is set to automatic and controls smoothly until the following upset in the process happens. The burner control linkage is extremely worn and loose. Based on this problem, what would you expect one of the symptoms to be?
What do you think, Jesus? Extremely worn and loose linkage.
It'd have to have happened over time, I believe.
I mean, yes, but I guess, yeah, like that makes sense that would have happened over time. But at this current point, we have extremely worn and loose equipment. So how is it going to handle at this point?
For symptoms for the process of this question, think it had dust buildup and that dust buildup suddenly fell out of the little ball joints and they're loose as a goose right now. They worked perfectly good this morning, but now that dust fell out and it's loose as a goose.
Mm-hmm. It would be hunting for its set point, I think. I guess.
All right, it pushes the fuel valve open from 0 to 7. 7's where you want to run. Now it calls for some more fuel. Well, the actuator starts moving, but the linkage doesn't move right away. Also, now it wants to cool down. Well, the actuator starts cooling it down, and all of a sudden it moves, and the slop is out of it now. Now it's pulling finally. So it's going to be moving back and forth hunting, but with that slop in there,
Okay,
it's likely to overshoot.
Okay, so it'd be
So-
hunting for it slowly.
Depending how sloppy it is and how tightly you've got your automatic controls set, slowly might be the right answer.
It's probably going to be
What-
quickly, I think, because of they're extremely worn and loose. So I think it's just going to be constantly moving position because it's never hitting the right position by the time it gets to where you wanted it and you want something else now. Or it's just going to, you know, like this much movement didn't actually move any. So now I'm going to double that movement or whatever. I believe it's going to be quickly because you're just going to not be hitting what you're aiming for. So you're just going to be shooting all over the place.
The correct answer is E. The controller is hunting for its set point by too quickly opening and closing the actuator.
The burner control is set to automatic and
That's a
controls
good
smoothly.
indication. Once a week or so, when you walk around, you should check it. Just kind of reach over, shake the linkage, just see if it's reasonably snug. Or if you reach over and all of a sudden you got half the rod in your hand and the other half of the linkage stayed there, you know it's probably past the time it should have been replaced.
Burner control is set to automatic and controls smoothly until the following upset in the process happens. The aggregate dryer's discharge temperature sensing probe is no longer in the hot aggregate stream. In fact, it fell out on the ground. Based on this problem, what would you expect one of the symptoms to be?
What do you think, Nathan?
I think the controller would be hunting it, the set point too quickly.
If our temperature probe fell out on the ground, so it went from 312 degrees to 70 degrees, do you think it's going to be hunting?
No, it'd probably drive open quickly.
Yep.
Now, I'm going to be a really nasty person, poke holes in this. If the temperature probe fell out on the ground, quite often, I don't care. It's charting on the chart for the state. That's the only reason it's important. I'm controlling off my stack temperature. For purposes of the question, though, you're controlling off material probe.
But it does say the discharge temperature probe, but it's not really saying, oh, in the hot aggregate stream. Yeah.
Yeah, it's saying aggregate, not stack.
Yeah.
I don't know who would go off their aggregate over their stack.
Depending upon how the plant works, some plants you get a better feel, especially in parallel flow.
Oh, yeah.
Yeah.
The correct answer is B. The burner actuator drives open quickly as indicated by the burner position indicator. Scenario. The burner control is set to automatic and controls smoothly until the following upset in the process happens. The automatic exhaust fan damper control is causing the damper to excessively hunt for the right suction pressure at the front of the dryer. Based on this problem, what would you expect one of the symptoms to be?
Not even sure I'm on. Nathan, did I just get you or am I on you?
Yeah, you just got me. I can do it again if you want me to.
All right, let's go 2 in a row.
All right.
Our damper is hunting around, it's opening and closing excessively. What is that gonna do to our burner?
I think the controller would be hunting for its set point too quickly.
Nice.
The correct answer is E. The controller is hunting for its set point by too quickly opening and closing the actuator. Scenario: the burner control is set to automatic and controls smoothly until the following upset in the process happens. The temperature controller's sensitivity adjustment, proportional band gain, is set slightly too low. Based on this problem, what would you expect one of the symptoms to be?
What do you think, Isaac? Sensitivity slightly too low.
Slightly too low, so slowly gonna open.
I think we're gonna get some hunting because it's gonna be slightly too slow in both directions.
Okay.
There again, have the readings written down.
The correct answer is F. The controller is hunting for its set point by too slowly opening and closing the actuator.
The burner control is set to auto.
The burner control is set to automatic and controls smoothly until the following upset in the process happens. The burner control linkage is slightly worn and loose. Based on this problem, what would you expect one of the symptoms to be?
Jesus. Now our linkage is just slightly worn and loose.
Okay. Well, I'd still think it'd be hunting and quickly opening and closing.
Yeah, I think we're gonna say it slowly this time. It's definitely gonna do some hunting.
Okay.
It's sloppy, but it's not drastic. You couldn't pull the rod end off the ball joints by just looking at it.
The correct answer is F. The controller is hunting for its set point by too slowly opening and closing the actuator.
Damper type closed loop control. Asphalt flow is controlled by adjusting the position of a valve in each
3.12 ton per hour by the controller signaling 2 volts DC to the motor. Suddenly, the oil percent indicator reads 0. The ground man reports the pump running full speed and the flow meter is turning at a very high speed. What are some of the possible causes?
Nathan, what do you think?
My screen. Oh, there it goes. I believe it'd be A, B, and
Nathan,
yes.
how are you going to pump air? If I'm indicating 0 speed
Right.
and the pump's running full out, is the
Well,
amount of
wouldn't
asphalt going to have anything to do with that?
the amount of asphalt?
Yeah, it's in the tank.
Well, I don't know. I said that because we ran when we ran out of asphalt oil in our vertical tank one time, and the tons per hour fluctuated from 0 to like
All right,
1
this
point.
isn't fluctuating. This is running, indicating 0.
Okay. And I
So the
believe
first
it
place
could be
tacks off the shaft, okay?
right.
Now,
Yeah,
is the amount
that
of
could be.
asphalt in the tank going to have anything to do with it?
No, B doesn't. No.
Okay. How about C? The electrical connector attached to the tachometer fell off.
Yes, that could be a possibility.
All right. Circuit breaker on the motor's tripped. Oh, wait a minute.
No,
Motor's
because
running flat
no, yeah, it's still running.
out. Okay. Frequency to voltage converter failed to provide a voltage signal to the controller.
That could be a
Possible.
possibility.
Set point signal from the percent oil to the belt scale tons per hour changed from 3.5 or 3.12 to 20.
No, I don't believe so.
All right, so we've got A, C, and E, correct?
Yes.
All right. I think we're right.
The correct answers are A, C, and E. A symptom of any output command signal from the controller going to the maximum output, such as 10 volts DC, and the process variable input going to 0, is an indication that something in the electromechanical feedback portion of the closed loop circuit has been broken. The asphalt tank running dry is not an indication because the air being pumped through the meter would turn the meter, but not at full speed, and the oil percentage indicator would be reading some random indication. The motor circuit breaker tripping would not allow the motor to run. The AC oil belt scale circuit is not a candidate because the oil percent indicator would still be reading the oil flow. The
That
asphalt
self-leveling
oil
asphalt.
flow.
So your mentioning of the fluctuation is the same thing he
Yes.
said in the answer to the right question.
Yep.
So,
That
and
that
when you
had
ran out
answered.
your tank dry,
Yeah, that explained it.
Flow rate, process variable,
Steve, can you hear me?
dropped slightly.
Yeah, we can hear.
Yes. Go ahead.
Yeah, Steve, if you got a micro motion meter, meaning there's no moving parts on your meter, you run out of AC, your meter will run wide open on a micro motion Emerson equipment. I've had
Yep,
that happen
I've
many
seen that
times.
before. Yep, I've seen that before.
On a micro motion, it'll run it wide open because you have no moving parts in your meter other than the vibrating coils.
Other than the measuring tube
So-
inside that is vibrating.
Yes, they're vibrating, but you can't see it. Anyway, I got a phone call, but no, a micro motion, it'll drive it wide open.
Okay.
From 3.12 to 2.92 ton per hour. In this application, how should the controller be programmed?
Jesus, what do you think?
Should make minor corrections over a period of time.
I think it's going to be instantly on this. I think it's going to be a minor correction instantly because just the oil is just an instant correction. You know, just a slight adjustment is going to give you more oil.
Response. It's not a long feedback loop. It's almost instantaneous feedback loop.
Yeah, it should be instantaneously.
The correct answer is C. When the asphalt oil flow rate, process variable PV, drops to 2.92 ton per hour, the controller shall make corrections to be done instantaneously. Whether the corrections are major or minor depends on the delay time of the electromechanical system making these changes. These changes in flow are near immediate, therefore making minor corrections instantaneously is proper. QC reports to plant management that the asphalt content varies high to low. Select any and all of the following problems which may be present.
What do you think, Nathan?
What my screen's, oh, there it goes. I don't know why it does that.
because it's buffering and you and I are out in the boonies and it doesn't like us.
Yeah.
Yeah,
I get the same way at
I'm right outside of the city limits right here at my job. So
Don't feel bad. Mine's acting the same way.
all right.
All right.
Asphalt content varies
Say-
high to low.
Saying it's going varying high to low on the asphalt content. What do we
Is
think
it
the problem
is it talking about the material or the actual oil?
The oil content is going from high to low.
Okay.
All right, would the scale idlers not being aligned affect how the belt's weighing?
Yes, it could.
Okay. Is it possible that the scale load cell has been overstressed
That's a possibility as well.
and sending in a flaky signal?
Right.
Okay, how about material buildup in the conveyor belt?
Yes.
The mud, that changes dramatically.
Yep.
All right, buildup around the load cell mechanism.
Yes.
Load cell wire connections being poor. Could be you got moisture in it.
Right.
So Billy.
And
Moisture in aggregate changed.
yep. I think it's all of the above.
How about G, asphalt pump sucking air?
Yes.
I can see an argument for all of them, Dave.
Right.
All of the listed issues are possible causes of the problem. What your instrument should read. Being instrument rated and certified depends on being competent. Only conscientious, knowledgeable people are capable of making low-cost, high-quality mix safely. Be one of them. When you show up for work, be there. A true story of a veteran operator, the moisture compensation set point was mistakenly set to 50% instead of the required 5%. The 200 ton per hour wet aggregate the belt scale indicator reports to the blending control will be interpreted as 100 ton per hour dry aggregate. This will affect the oil content being proportioned. The mix will be A, extremely rich, or B, extremely lean.
What do you think, Isaac?
Extremely lean.
Because we're putting in
The
enough
correct
oil for
answer is
100
B.
into 200.
The computer is putting enough oil for 100 ton per hour into a mix rate of twice that much. Consequently, the mix had 2.5% oil, making the mix appear brown and not black. The old saying was to make it hot and black. The operator was sending brown mix out to the paver. The paver was refusing to lay it down.
Now, in this case, the lab is right. On that other case, one of the possible things that could have been is how is their sampling? Do they have a sample that is running consistent on gradation? Or is gradation one sample very coarse and the next sample very fine? Because that will also drive the asphalt content off both ways. If it's extremely coarse or extremely fine, that'll vary it from the perfectly blended mix you're trying to ship out. So question the sampling. If the gradation is correct, then yes, believe the asphalt content being off.
Yeah, be aware if they change out testers that your testing results will change.
Sensor falls out of the well in the asphalt pipe. The sensor normally reports to the computer that the temperature is around 300 degrees, but it is now reporting 75 degrees when the oil is actually 302 degrees. This will affect the amount of oil the computer thinks is going into the mix. Consequently, the closed-loop control action of the computer will correct the speed of the pump based on this bad information. How will the mix be affected?
This is assuming that it is a volumetric type measurement.
What do you think is going to happen, Jesus? We have 302 degree oil, but our computer thinks it's 75 degrees. We have colder, heavier, or we have thinner, lighter oil than the computer thinks. The computer thinks we have cold, heavy oil.
It should be more lean. It'd send more in.
The correct answer is D. The lower temperature being reported makes the computer think heavier oil is passing through the volumetric meter. Consequently, it forces the pump to slow down, pumping lighter 300-degree oil. The strainer lid on the suction side of the asphalt pump is loose, and consequently various volumes of air are being drawn in and passed through the meter. What are all the applicable symptoms to the asphalt metering problem?
Nathan? Strainer lid on our asphalt pump is loose. I'm pumping some air.
It'd be A, B, and D.
I don't know that it's going to be rich. We're putting some of what it thinks is going through is air, but it thinks it's oil going through us, taking up some of the volume. So I don't think it's going to be rich.
Oh, okay. So lean, A, C, and D.
I think that's where we're at.
Sounds good.
The correct answers are A, C, and D. The meter will be metering air almost as if it is oil. Consequently, the meter will measure inconsistent amounts of oil. Asphalt oil content is significantly out of tolerance. The oil closed-loop control gets its ratioed set point from the belt scale. Choose all of the following that may be contributing to this error.
What do you think, Isaac?
Okay, so the speed sensor on the top left is positioned just a little too far from the metal tab rotating near it. Yeah, I guess I'd say A could be an option. I mean, if the hinge mechanism on the bottom belt scale is over torqued. B, the belt is shifting from center to the right as the belt is being loaded. That could be an option too. C, it's a very windy day. Winds crosswind, skip. D, I'd leave E out.
No leap year for you.
No.
The correct answers are A, B, C, and D. The speed sensor on the top left is positioned just a little too far from the metal tab rotating near it. The hinge mechanism on the bottom belt scale is over-torqued. The belt is shifting from center to the right as the belt is being loaded, or it is a very windy day and the winds are crosswise to the scale conveyor. The asphalt mix is varying between too rich and too lean. The scale will not return to zero. All the normal housekeeping checks have been pulled on the belt scale. Short of checking the scale idler alignment, the load cell should be suspected of being overstressed over time. The hinge mechanism being aged or over-torqued has this same symptom. The following are steps to determine if the problem is with the load cell or the weighbridge mechanism. They may not be in order. If the analysis shows the test weight addition is not linear compared to the rate, the load cell or hinge mechanism should be heavily suspected. Check that the hinge mechanism is in good shape and not over-torqued, then consider replacing the load cell. These steps are assuming proper lockout procedures are being followed. A true story, the ground man was carried into the head pulley when his coat was snagged by belt clips. Place these steps in the order they should be carried out.
What do you think, Jesus? We got four steps here in column 2. What do you
I'd
think we should
start
do
by
first?
taking off all the weights and zeroing out the conveyor belt. So
So we're assuming we don't have any. We're starting out, there are no weights on there. So we probably don't want to start out with taking off weights, because we haven't even put any on there.
okay. Well, then you would zero out the conveyor belt, start up the conveyor belt and zero it out. See,
There you go. You want to zero it in running condition. So we want that conveyor running before we zero that scale out.
okay. And then
This is a good starting point.
you would add weights on, see if they match up to the conveyor belt.
Nice.
Uh,
I guess
confirm.
you kind of gave it that, yeah. Confirm that
Yeah.
they went up, they increased proportionally.
And then B, take all
Nice.
of them off.
Good job, thank you.
Place these steps in the order they should be carried out. The correct order is C, A, D, B.
Hmm.
5.5% oil in it. The mix calls for 5.5% oil. Quality control finds a problem. Actually, the problem they find is a symptom of another problem causing the symptom they are reporting to the plant management. The real problem is that the mix is segregating. QC is sampling the mix out of the truck. The sample they are taking is very rocky with very little fines. QC tests for asphalt content and finds the mix A, rich, or B, lean.
What do you think, Nathan?
It'd be lean.
Nice.
The correct answer is B. The mix is too lean. The easiest way to explain where most of the oil will be is by making a comparison. A box of rocks and a box of sand are available to clean up an oil spill. The sand is a material that holds more oil because sand has more surface area than rock.
The system is reacting to your lime silo vane feeder feeding the flow scale. The tons per hour indicator reads the same as the set point. Therefore, the controller maintains the motor speed as is. The system is
Too much material is being added to the mix. How do we prevent problems and troubleshoot while operating? Choose all that apply.
Isaac, what do you think?
Okay, so too much material.
So that first one is pretty much saying it, comparing your flow scale. So you have a flow scale being fed by your dust auger. So if you're normally running your dust auger at a certain speed, and you know this is what our scale says at this speed, you know, you can kind of have a volume, or it's if it's calibrated volumetrically, but in that scenario, it's probably not. But if you have an idea, so like Steve was saying, write down things when things are working. It's good to have, know how they're working. When you're normally running 10 tons per hour of dust into your mix, you probably have a good idea of what speed you're running at when you do that. So if it starts to widen out or become different than that, then that's probably a good check to do as you're running. That can kind of tell you your scale's not lying to you.
Okay.
So do you think that's a good idea to kind of compare your scale and a volumetric rate?
Yeah. Yep.
So you can find out on the fly. Constantly inspect for proper operation, venting, continuous flow in and out of the scale or internal buildup.
Yeah. Yep.
I could throw your mix, the material being added off. Compare material used with scale totalizer. It's probably not always the easiest thing to do, but in some cases, like when you're adding fiber to your mix or something, if you know you're throwing in 40-pound bales, if you keep track of how many bales you threw in, then you have something to compare to.
Okay.
We threw in 800 pounds of fiber and my scale says 789 pounds went through or whatever, you'll be able to tell pretty closely, is my scale pretty close or is this isn't adding up?
Okay.
Make sure the auger motor is turned on.
Yep.
That's probably not going to give you too much material.
Oh, too much material. Yeah, take material away. Yep. Turn off material. I'd say A, B, and C.
E is always a really good check on your scale. Whenever you shut down, you always want to check and make sure your scale is going to 0. That's like checking before you step on your bathroom scale to make sure it doesn't say 20 pounds.
Okay.
Because if it does, it's not, you can't believe what it's going to say when you step on it.
Right. Okay. Well, that makes sense.
The correct answers are A, B, C, and E.
Modern blending controls monitor many set points and compare them to the.
That was it. We just burned through all those questions.
You guys think of some more questions for us while you've been suffering from us asking you?
No.
Isaac, what type of asphalt pump have you got? Is it volumetric?
It is. Yep.
How about you, Jesus? What do you got?
Honestly, I have no idea. I don't really run it quite yet.
Is it kind of like a Viking pump out with a motor on and then a Viking pump with just a sensor on it?
Yeah, it's got a motor and it pumps, but
Okay.
I don't know how it measures it.
What they're doing there is they're taking and they know how much volume is in that pump when it turns a revolution. So you've got the pump with the motor that's forcing the asphalt into the line or into the next pump. And then you're counting the speed and the temperature on that pump and comparing to what you think you should have.
Oh, okay.
Because you know, every revolution of that pump is going to give them, like, say, 7 pounds of oil, or it should have, like a gallon or a gallon and a half, and that should weigh X number of pounds. And at that temperature, you do a temperature correction because the hotter it is, the thinner it is, the less it weighs. So that's how that system works. It's counting that little tachometer on there has actually got like a little glass disc on it, and it'll tell you how many pulses per revolution, like 12,000 or 1,000 pulses, little individual lines will go past the sensor. And that signal train is coming in as a frequency. Well, the computer's set up to tell the frequency of, okay, this went around how many times in a minute or how many times in an hour. Each revolution is supposed to weigh so much, and I'm correcting for what temperature. That's how the magic happens, that it tells you so many tons per hour.
All right. Yeah, I don't really feel a whole lot on that end, so this is all
The simple explanation is it's a black box. You feed information in, you get information out.
Yeah.
The information you're feeding in is RPM and temperature. What's coming out is tons per hour. We're supposed to.
Okay.
And you know enough now to look and see, am I putting all oil in or am I putting air and oil in? Is the speed tack in the, hooked up and running, giving me a signal? Is the temperature probe in its well and giving me a signal? That's what you need to look for.
Okay.
Nathan, what have you got? A pump and a pump?
Yes.
You don't have a Brooks anymore, do you?
No.
Good. They're getting hard to fix. Isaac, you got any other questions here?
Oh, I don't. Nope.
Jesus?
No, I think we're all good on my end.
Nathan?
No, I think I'm good.
Jeremy?
I can't think of anything else.
How about you, Dave? You've usually got one or two hit away.
I just had, I don't know, Clarence wanted to throw these out there.
Well, what I would like to say is you guys been with Steve for about 6 damn days here. And let's have a round of applause for you guys being around Steve for 6 damn days. Good job. And then you're around with David for about a half a day today, and you're around with Jeremy for a day yesterday. Me for maybe a half a day or 3/4, what the hell ever that was. Anyhow, I hope you guys are different now that you've invested all this time into that, and I'm sure you're going to get your money's worth. You just gotta keep after it. I'm glad you're here. I think you're pointing off in the right direction. As you can see, we got some certificates that's going to go out. You guys should be keeping those, and you should be giving a copy to your company HR person. Say put that in your personnel file. You guys have spent a lot of time with safety. If there's an accident around the plant, OSHA's asked for if there's anyone that has safety training. You can tell them you have had safety training, and it's really good training there for the plant. So based on that, it sounds like you guys are kind of full up, and now you want to get ready to start doing some maintenance on your plant. Go for it. You can have some safe maintenance now. That's all I got. Thank you very much. I appreciate the opportunity to share the information we have collected over the years. We've been doing this for about 30 years now. Not quite, but anyhow, thank you very much. I think the Zoom meeting kind of made it easy for us to get to. We didn't have to jump on a plane, and we still got a lot of good information out of it. So I think we did damn good. So that's my story. I'm sticking to it. David, why don't you pull up one of those certificates?
Oh, were you not seeing them? I was kind of looking
Okay,
through 'em.
well, we're back to you again. Okay, so it looks like Isaac, you get one. You work with Rochester Sand and Gravel, so of course you work with that Kenny Yeager, of course, right?
Yeah, I know Kenny.
Okay.
Yep. Good dude.
Okay, well, tell Kenny we say hi. It looks like you stayed with us every step of the way. I haven't been to your plant in the longest damn time. I remember your plant being a batch plant way back when. That shows how long I've been in this business. It was a Barber Green. So Isaac, thanks very much for being here. Who else we got besides Isaac?
We got Jesus.
Let's take a look what Jesus gets. Looks like you get the same thing, Jesus, and you're with Harris Sand and Gravel. Are you guys out of Kansas? Where are you guys out of, Jesus?
Valdez, Alaska.
Alaska, no kidding.
That's why when we kick him loose clearance, he'll finally be able to go get lunch.
Yeah. Yeah.
Okay, that's
Okay.
what you're talking about, scrubber and all that stuff.
Yeah.
I can understand. We've done a couple workshops up there in Alaska. It's pretty cool up there. I know sometimes you don't get any support, so you're the last guy on the totem pole to make it work, because you're just out there So if you get a portable plant or just a stationary plant, Jesus?
Well, it's stationary, but we make it portable sometimes when we get big jobs. I mean,
Okay.
it can be moved, but we try to not move it. It's usually there
Okay.
for a couple of years until we do.
Okay, well, when you go out in the field, it really comes in handy to have a little bit of electrical background and talk to your people on what to do there. So congratulations there. And so besides Jesus, who else we got? We got Nathan, right? Nathan, you're with Fuller and Sense. Where's Fuller? Are you out east?
We're in Amarillo, Texas.
Okay, Amarillo, Texas, in the Panhandle. Okay,
Panhandle.
that's right. Uh-huh. Do you guys get a batch plant, or what kind of plant? No, you don't have a batch plant, do you?
No, we have a Barber Green.
Drum mix plant?
Yes.
It's an old
Okay.
DM55. That's the one that Phil helped them out on last year.
Yes, sir.
Okay. Oh, Phil gave you guys, oh, so Phil's working with you.
Yes, Phil worked with us for a while, and I think he's the one we actually got our new bins from, if I'm not mistaken.
I think he's working at the flow scale for you too, for your dust bin. Isn't that right?
Is
David,
We-
is it?
no.
We don't have a dust bin.
Okay,
No, this is a different job he's working. I can't remember who it is right now.
Okay.
Noble's Construction.
that's right. We're working with Phil's working in another company. They bought one of our dust flow scales so they could do a dust bin thing. I thank you for being here. AJ's been through a lot of our workshops before. How you doing, AJ? Thanks for coming in.
I enjoyed you having me. I did put my 2 cents in once. Hope I didn't
Okay.
use
Okay.
toe.
No, you
Okay.
didn't. That helped because I haven't been around those micro motion meters much.
Oh,
I mean,
they-
I don't work on that many CMIs, and the
Yeah.
last time I was really around them a lot was when I was working for Klausner moving lime slurry with them.
Well, like I say, they're a different animal. Air just drives them nuts, and they'll go to zero, and it makes the pump go faster. Again, like I say, there's no mechanical meter that you can see, just that Borealis tube, and just air. Any air drives them nuts, and an empty tank will make it pump go wide open.
Okay.
So
Okay.
Information I was not aware of, so it was greatly appreciated.
any a little I can help, Steve. It's good to talk to y'all, Steve. I haven't talked to you in quite a while, and Super Dave, been a pleasure. Jeremy, I'd like to tell you, hadn't met you till today, but and of course Clarence, my friend
Yep.
Clarence.
Yeah, well, thank you very much. And it looks like you're going to Con Expo. AJ and his wife Kim, are they going on their honeymoon at Con Expo?
One second. That's our honeymoon. Well,
Isn't that where we're gonna go? We take all our family vacations at Con Expo too. That means you got construction in your blood. It's
Yeah.
time to go see a doctor.
there you go. I've been to Con Expo for at least three other times. I forget. I've been there a few times. It's neat. Yeah, it's neat. Nice place to visit, but I wouldn't want to live there.
Yeah, okay.
For
Well,
the
gentlemen,
for the guys that haven't been there, Con Expo's got exhibitions set up. And the time I went, they had like 54 miles worth of booths set up if you went down and passed everything. So
bring your running shoes.
It's unbelievable. It's unbelievable. All the equipment. CAT usually has 3 displays. They had one time I was down there, they had a cross section of the 747 that they had put a D9 CAT in, and it's quite a.
Really?
Yep.
And where's that located?
What was
Las
that?
Vegas Exposition Center. And
Oh, yeah.
they'll
Las
have
Vegas.
one yard Aztec will set up a full plant.
Yep.
With multiple bends or multiple setups, actually.
Is that
Tuma
year
and the
round?
rest of them will do the same. It's once
they-
every 3 years, usually March.
Okay, I was just wondering.
If you get like the Asphalt Pro magazine or the Asphalt Construction magazines or Pit and Quarry, you should see notifications and such in there. I highly recommend that you guys get some of the trade publications. They're usually free, and there's a lot of good, useful information in them. Shoot,
Yep.
Dave, Clarence, and I even write for them occasionally. They
Occasionally.
get that hard up for articles.
Yeah,
Peer
Gencor
and
set up
landers.
100-ton
I was
silos.
wondering.
Go up the ladder.
I was wondering. I was going to Vegas in July, so I was.
Well, you
Exactly
missed
when
the
you
show.
don't wanna
They
be
should
in
have it
Vegas.
tore down by then.
Yeah, that's why I was asking where is that and stuff. So.
It's
Definitely gonna go
so
up there.
big. It's actually in almost all their exhibition centers. It's the largest show that they actually put on in Vegas. The number
Okay.
of people and the amount of area that it covers. It's in like 5 or 6 buildings and 3 or 4 different parking lots.
Yes.
It's impressive. I mean,
Large.
JLG will have like a 150-foot boom there. They'll have concrete pumpers there. You name it,
Yep.
you're likely to see it.
All the truck manufacturers, equipment manufacturers of all world, all over the world.
Additives and such.
One time.
One of the cool additives I came across one time was bean extract, soybean extract. And that's when they were really coming down on diesel first. And I've never seen lab equipment clean up site quite so well as using soybean extract that was actually edible on a salad safely. I mean, it's wild the different things you can run across there.
Oh,
They
yeah.
had with the
I don't know if
crushers and such, they've had like high pressure spray systems to put a fog in front of the crusher to keep the dust contained. You name it, it's likely to be there.
That's cool. I worked at West Amarillo Sand and Gravel for Rogers Group.
Oh, yeah, Rogers, got it.
Yep, I worked for them for about 2 years. I was working on the main plant, around the main plant, and they had showed me. I don't know if it was there, but they showed me a video of a Komatsu excavator that was remote controlled.
Really?
Yeah, they've got one of them they can drive on the bottom of a lake even.
That's crazy.
You can say that again.
A lot of food, a lot of free beer, a lot to see.
Free beer's good.
Well,
Free
anyway.
beer's good.
What's that, Clarence?
Free beer is good.
Free beer? What?
Yep.
I'm there.
I agree.
And just down the road for you.
Dave still owes me one too.
Yeah,
gonna
I
get
know.
out of
I probably owe you a couple.
I'm gonna get out of
Hey.
here.
Margs.
Invite me.
Say, Dave, when
I
are
hope
we
so.
supposed to expect that steak being delivered?
Oh, I did. You guys were supposed to show up yesterday. I told you guys I was getting the grill going.
In Fargo, North Dakota. Huh?
It's
The
warm. It's
freeze
warm
dried.
enough to fire up the grill, Dave.
No, it's not even close to warm enough.
Oh hell!
Yeah, I'm pretty sure they would just get colder if I.
Well, again, Clarence, it's been a pleasure.
Okay, well, AJ, nice seeing you. We'll keep in touch with you.
I will.
I'll stop by and see your new controls.
All right. We should be going middle of April at the latest, I hope. So
Okay,
we'll see you
Well,
then.
okay,
you.
talk to you later. Gentlemen,
Yep.
if that's all you got, that's all I got.
Well, I got.
Yeah.
How about you, Jeremy? All you got?
That's all I have. I ain't got much, but that's all I have.
You did
Well,
mighty
the-
fine, mighty fine.
Well, the
Use
certificates.
the
that you
email for
sent
your question.
Yeah, we'll mail them to you.
to the company or to our home address.
What would you rather have?
Either you could mail it to my home address.
That way you know you'll get it.
Yes, sir.
Do you know Carrie's email address?
Who's?
Carrie.
Carrie? No.
You can just send it to me, Nathan. You have mine,
Okay.
right? I've been emailing you the links and stuff.
Okay, how about you other guys? You
Yeah,
want
no,
to go to your home address or do you want to go to the office?
No, whichever address you got for me, I'm good with that.
I'm fine either way.
Okay. Okay, well, gentlemen, it was nice meeting you.
Yeah,
I think I
appreciate
don't, I think I don't care what Ken Jagger says about you. I still like you.
Hey, thanks a lot.
You'll just
Okay,
email
I'm outta
my
here.
address to
See
you,
ya.
Dave?
See you, Steve. Thanks for everything.
Yeah,
All right, thank you.
guys.
Later, guys.
Later.
And guys, remember you've got emails and such to ask for questions later on. And go ahead, Nathan, you've got a question or something going there.
Do I send Dave my home address, or what am I sending to him?
Yes.
Whatever,
Your
yeah, whatever you want the certificate sent.
Your mailing address should go to Dave.
Okay, that'll work. Thank you, guys.
Yeah, thank you.
Okay,
And if you can take my email and send me a photograph or so of your burner control close up, then we can discuss later on if you want to send that up. Give me a phone number to call and we can talk about it, okay?
Okay, I'm not sure I have your email, Steve.
SHKLEIN 56 at gmail.com. That's S as in Stephen, H as in Herbert, Klein,
you may have
KLEIN
frozen up.
56
All right, I
Uh,
got it.
Okay,
at gmail.com.
That'll work.
And
Thank
if
you.
you need to send me a text, 608 633 5738. That's my cell phone, and that's good for text.
All right, that'll work. I appreciate it.
And put your company in the subject block and header or question so that I know that it's not trash mail and will be immediately stuck in my spam folder.
Okay,
You stand a chance of getting a hold of me that way.
that'll
Quit
work.
snickering, Jeremy. I know you do the same.
Oh, yeah.
Well, guys, thank you very
All
much
right.
for showing up. It's been a pleasure teaching you guys. And really, thanks a lot for the questions, because the more questions you ask, the more detail we can go into, and the easier it is sitting on this end of the screen teaching than just trying to come out of everything out of your head.
Right, like I said, I've learned a lot going through this course, and I've learned a lot about the stuff that needs to be fixed around here.
Talk to the two guys who went through it last year. And
But, they're
between you
actually
all,
here.
say again?
Steven and Chris Melendez, they're actually here working on the plant with us.
Excellent. Talk to them because they went through the same class and such, but every class and every day is different. We'll try to cover all the same subjects, but depending upon what the questions are, we cover it differently each time. And as you've seen, Jeremy, Dave, Clarence, and I all teach somewhat differently. We all have our pet peeves that we try to
Right.
cover. So you're going to get the same basic information, but the stuff that really drives us up the wall is what we're going to concentrate on. And if we get your questions to try to clarify where we should be headed, it helps a lot. So,
All
on that
right.
note, you guys, great effort, and I'm out of here.
Yep.
All right. Thank
See
you.
you guys.
Thanks a lot.
Watch out for
Thanks.
that train, Steve.
invite, man. Thanks, Dave.
All right. Oh.